You've been lied to. Not deliberately, not maliciously, but lied to nonetheless. Every documentary you've watched, every science book you've read, every classroom lecture about the origins of everything, they all told you the same story. The Big Bang, the moment of creation, the beginning of time itself, compressed into an infinitesimal point, exploding outward in a violent cascade of energy and matter, birthing galaxies and stars and planets, and you. It's a beautiful story, a cosmic genesis, a scientific creation myth that satisfies our deep, primal need for beginnings. But here's what they didn't tell you. The Big Bang didn't bang. Let that sink in for a moment. The most famous event in cosmic history, the foundation of modern cosmology, the very moment we point to when someone asks how everything began, it's not what you think it is. Not even close. And if you're feeling a slight vertigo right now, a subtle shift in your understanding of reality, good. You're beginning to see the edge of something vast and terrifying and absolutely profound. You're approaching the boundary where physics itself starts to stutter and break down, where our most brilliant equations dissolve into mathematical gibberish, where the very concept of before loses all meaning. This isn't just about cosmology. This is about the limits of human knowledge. This is about standing at the precipice of the knowable universe and staring into an abyss that stares back with silence. Because here's the uncomfortable truth that keeps physicists awake at night. When you ask what came before the universe, you're not asking a question that has a difficult answer. You're asking a question that might not even be a question at all. Imagine you're watching a movie. The opening scene appears on screen. A character walks into a room, sits down, begins to speak. Now pause it, rewind it. Watch the character walk backward out of the room. Keep rewinding. Past the opening credits. Past the production company logos. Past the black screen at the beginning of the file. What comes before the movie begins? But those things didn't happen before the movie. They happened before the movie existed as a finished product, yes. But they're not part of the movie's timeline. They're external to it. They exist in a completely different framework. Now ask yourself, what's on the video file before the first frame? Nothing. Not darkness, not silence, not empty space, nothing. The concept of before doesn't apply to the movie's internal timeline. Time, within the movie, begins with frame 1. There is no frame 0. There is no negative time. This is closer to the truth about the universe than any creation story you've ever heard. But it gets stranger. Right now, in this moment, you exist in time. You have a past, memories of yesterday, last year, your childhood. You have a future, plans for tomorrow, dreams for next decade, hopes for the years to come. Time flows around you like an invisible river, carrying you from moment to moment, second by second, always forward, never back. This experience of time feels fundamental. It feels like the most basic aspect of reality. Of course, there's time. Of course, there's before and after. Of course, there's cause and effect. Except at the beginning of the universe, there wasn't. At the singularity, that impossible point of infinite density where all of existence was compressed into something smaller than an atom, smaller than a proton, smaller than anything with physical dimension, time itself breaks. Not like a clock stopping, not like a pause button being pressed. Time breaks the way a mathematical equation breaks when you divide by 0. It doesn't just stop. It becomes undefined, meaningless. And when time becomes meaningless, so does every word you use to describe temporal relationships. Before, after, cause, effect, beginning, end. All of these words are time words. They only make sense when time exists. You're doing something subtle and strange. You're trying to apply a time word to a situation where time doesn't exist. You're asking what's north of the North Pole. You're asking what happened before time began. You're asking a question that contains its own impossibility. And physics can't answer impossible questions. But let's not get ahead of ourselves. Let's start with what we think we know. You've seen the images, the deep field photographs from Hubble and Webb, showing thousands of galaxies scattered across the cosmic dark like luminous grains of sand, each one containing billions of stars, each star potentially harboring worlds of its own. The scale is incomprehensible. The numbers are almost offensive to human intuition. And it's all moving, expanding. Every galaxy racing away from every other galaxy, like pieces of cosmic shrapnel frozen in the moment after an explosion. The farther away a galaxy is, the faster it's receding. This is the cosmic expansion, discovered by Edwin Hubble in 1929, and it's the smoking gun that points backward to something extraordinary. If everything is moving apart, then in the past, everything was closer together. Rewind far enough and all of space collapses down to a single point. All the matter in the universe, every atom in every star, every particle in every galaxy, everything that is or ever will be, compressed into a volume of zero. Infinite density, infinite temperature, the singularity. 8 billion years ago, it began to expand. Not into pre-existing space, this is crucial. The universe didn't explode into an empty void. Space itself expanded. Time itself began flowing. The universe didn't happen in space and time. The universe is space and time. This is the standard model, the cosmic concordance, the most successful scientific theory about the origin of everything. It's supported by multiple independent lines of evidence: the cosmic microwave background radiation, the abundance of light elements, the large-scale structure of galaxy distribution. It fits the data beautifully, and it's completely, maddeningly, infuriatingly incomplete. Because when you trace backward to that moment of infinite density, something catastrophic happens to physics itself. All of our equations, our elegant mathematical descriptions of reality, start spitting out infinities, not large numbers, not quantities beyond measurement. Actual mathematical infinities. And in physics, infinity isn't a number. It's a signpost that says, your theory has broken down. General relativity, Einstein's masterpiece, his geometric description of gravity as the curvature of space-time, predicts the singularity. But at the singularity, general relativity predicts its own failure. The curvature becomes infinite. The equations produce nonsense. Einstein's theory is telling us, I can't work here. Quantum mechanics, the bizarre, probabilistic rulebook governing the subatomic realm, should step in. At the smallest scales, quantum effects dominate. Particles blur into probability clouds. Energy fluctuates in and out of existence. The rigid, deterministic clockwork of classical physics dissolves into a haze of quantum uncertainty. But quantum mechanics was developed to describe particles and forces, not space-time itself. When you try to merge quantum mechanics with general relativity, when you attempt to create a quantum theory of gravity, the math explodes. The calculations produce infinite answers to finite questions. The theory eats itself. We have no complete quantum theory of gravity. No unified framework that works at both the cosmic and quantum scales. No mathematical language that can describe what happens when all the matter in the universe is compressed to a point smaller than the Planck length, the smallest meaningful distance in physics, approximately 10 to 35 meters. At the Planck scale, space and time themselves become grainy, discontinuous, maybe even meaningless. Our smooth, continuous space-time might be an approximation, a large-scale average of something far stranger happening at the quantum level. Some theories suggest space-time is woven from quantum threads. Others propose it emerges from even more fundamental quantum information. Some suggest it's an illusion entirely. And this is where physics breaks. Not breaks like a machine that needs repair, breaks like a concept that reaches its natural boundary, like asking what's south of the South Pole, like asking what English word rhymes with orange and means exactly the same thing. The question itself is malformed. When you ask what came before the Big Bang, you're assuming time extends backward infinitely, or at least backward beyond the Big Bang. But what if it doesn't? What if time is like the surface of the Earth, finite but unbounded, with no edge, no beginning, no before? Stand at the North Pole. You can walk in any direction, and you'll be walking south. There is no north from that point. The concept breaks down, not because you're ignorant, not because you haven't looked hard enough. Is asking for something that doesn't exist. This is the situation with the Big Bang. Time might begin at that point the way north begins at the North Pole. There's no before, because time itself doesn't extend beyond that boundary. The universe isn't inside time. Time is inside the universe. But your mind rebels against this. Of course there's a before. There has to be. Everything has a cause. Everything comes from something. To say there's no before is to say the universe just appeared, uncaused, from nothing. And that sounds absurd. That sounds like magic, not physics. Yet here's the twist. The idea of causation, the entire concept of one event leading to another, is itself a feature of time. Causes precede effects. The word loses meaning. You can't have a cause without temporal succession. You can't have a before without time to put it in. So the universe might not need a cause, not because it violated some law of causation, but because causation itself doesn't apply at the origin of time. It's like asking what caused the number 3. Numbers don't have causes. They're not events in time. They just are, existing in a logical, mathematical sense that transcends temporal flow. Maybe the universe is the same. Maybe it simply is, existing not in the sense of persisting through time, but in some timeless, eternal, mathematical sense. Maybe the Big Bang isn't the moment when the universe was created, but the boundary beyond which time doesn't go. And maybe, just maybe, that's not the end of the story, because physics doesn't give up easily. When one theory breaks, physicists build new ones. When reality seems impossible, they revise their understanding of possible. And in the past few decades, they've proposed some of the most radical, mind-bending ideas in the history of science. What if the Big Bang wasn't the beginning? What if it was a transition? What if our universe emerged from the collapse of a previous universe? What if there are infinite universes, each with its own Big Bang, bubbling into existence like foam on an infinite cosmic ocean? 8 billion years ago, but merely underwent a phase transition. The way water changes from liquid to ice? These aren't science fiction speculations. These are serious theoretical proposals, each grounded in rigorous mathematics, each attempting to extend physics beyond the boundary where our current theories break. But here's the thing they all have in common. None of them can be tested. Not yet. Maybe not ever. You see, we can observe the universe as far back as the cosmic microwave background, the afterglow of the Big Bang, visible in all directions, a faint whisper of radiation from 380,000 years after the beginning. Before that, the universe was opaque, a hot, dense plasma that light couldn't pass through. We can't see beyond that veil. We can't observe the first fraction of a second directly. And the earlier you go, the more extreme the conditions become. The hotter, denser, more energetic the universe was. To test theories about the Planck era, that first 1043 seconds, you'd need particle collisions at energies that dwarf anything we can produce. You'd need to recreate conditions that haven't existed since the first instant of cosmic history. You'd need to build a particle accelerator the size of the solar system. So we're left with mathematics. Pure thought. Elegant equations that describe realities we can never touch, never see, never directly confirm. We're left with theoretical physicists staring at blackboards covered in symbols, arguing about whether their equations describe the actual universe or just self-consistent mathematical fantasies. And yet, despite all these limitations, despite the broken equations and untestable theories and fundamental barriers to knowledge, physics keeps pushing, keeps probing, keeps asking what came before, even when before might not exist. Why? Because we're human. Because curiosity is encoded in our species. Because we look at the stars and feel a deep, aching need to understand how they came to be. Because we stand on a tiny rock orbiting an ordinary star in an unremarkable galaxy, and we dare to ask questions about the origin of all existence. There's something simultaneously humbling and audacious about this. We are, in cosmic terms, nothing. Fleeting arrangements of atoms that briefly light up with consciousness before dissolving back into the universal dark. 8 billion years old. Human civilization has existed for perhaps 10,000 years. Your individual life is maybe 80 years if you're lucky. You're a spark. A momentary fluctuation. A brief local decrease in entropy before the cosmic heat death swallows everything. And yet here you are, reading these words, contemplating the origin of time itself. A collection of atoms arranged in such a specific way that you can ask questions about the arrangement of all atoms everywhere. A pattern of matter and energy complex enough to wonder about the source of all matter and energy, the universe contemplating itself, existence asking about its own beginning, the cosmic asking about the origin of the cosmos. This is the paradox at the heart of everything. We're tiny and insignificant, and yet we're the only things in the known universe capable of understanding our own insignificance. We're brief and temporary, and yet we can conceive of timelessness and eternity. We're limited and mortal, and yet we can imagine infinity. And when we ask what came before the universe, we're not just asking about cosmic history, we're asking about the limits of understanding itself. We're probing the boundary between the knowable and the unknowable. We're standing at the edge where human comprehension meets something vast and other and fundamentally beyond us. This boundary has a name in physics. It's called the Planck epoch, the first 10 to 43 seconds after the Big Bang. A time interval so short that if you divided 1 second into pieces, you'd need more pieces than there are atoms in the observable universe just to count down to the Planck time. In that brief, inconceivable moment, the universe was smaller than an atom, hotter than anything that has existed since, denser than a neutron star by factors that make a neutron star look like empty space. And our physics doesn't work there, can't work there. The equations that describe everything else, gravity, electromagnetism, the strong and weak nuclear forces, all break down. They're like computer programs that crash when you input the wrong value. But physicists, being physicists, aren't content with dragons. They want to map the territory beyond the map. They want to know what happens when space-time itself becomes quantum mechanical, when gravity plays by quantum rules, when the smooth fabric of Einstein's universe dissolves into a foaming, bubbling quantum chaos. This requires a theory of quantum gravity, a framework that unifies the two great pillars of 20th century physics, quantum mechanics and general relativity. And despite nearly a century of effort, despite some of the most brilliant minds in human history dedicating their careers to this problem, we don't have one. Not a complete one. Not one that everyone agrees on. We have candidates. String theory, which proposes that fundamental particles are actually tiny vibrating strings in 10 or 11 dimensions. Loop quantum gravity, which treats space-time itself as woven from quantum loops. Causal set theory, which suggests space-time is made of discrete points connected by causal relationships. Emergent gravity theories, which propose that space-time and gravity aren't fundamental at all, but emerge from deeper quantum information. Each theory is mathematically sophisticated. Each makes novel predictions. Each offers a different picture of what happens at the Planck scale. And each is, so far, untestable. This is the crisis of early universe cosmology. We're trapped in an era where theory has outrun experiment, where our mathematical imagination has exceeded our ability to build instruments that can check whether we're right, where the most fundamental questions about reality, what is space, what is time, remain stubbornly, frustratingly unanswered. And this brings us back to you sitting here, reading this, existing in this moment. You're made of atoms forged in the cores of dying stars, the calcium in your bones, the iron in your blood, the oxygen you're breathing right now. All of it was cooked up in stellar furnaces billions of years ago, then scattered across space when those stars exploded. You're literally made of stardust. This isn't poetic metaphor, it's atomic fact. But those atoms came from somewhere too. Trace them back far enough, and you reach the first 3 minutes after the Big Bang, when the universe was a hot plasma of protons, neutrons, and electrons, fusing into the lightest elements, hydrogen, helium, a trace of lithium. Go back further, and you reach the first second, when even protons and neutrons didn't exist yet, when matter was a quark-gluon soup, an undifferentiated sea of fundamental particles. Further back still, microseconds, nanoseconds, picoseconds, after the beginning. And even the fundamental forces separate. Electromagnetism and the weak nuclear force, which appear distinct in our cool, low-energy universe, were once unified into a single electro-weak force. Go back to 10 to 36 seconds, and even the strong nuclear force joins the party. All the forces of nature might have been unified into a single, elegant, symmetric force. And at 10 to 43 seconds, at the Planck epoch, even gravity unifies with everything else. Or so the theories say. At that moment, the universe was simple, perfectly symmetric. All forces one force, all particles interchangeable. A state of such high energy that our current physics can't even begin to describe it accurately. This is the territory where physics breaks. This is the edge of knowledge. Imanseking makes sense, but let's push anyway. Let's ask the forbidden question. Let's violate the boundary and see what happens. What came before the Big Bang? Option 1. Nothing came before. Time began at the Big Bang. The question is meaningless, like asking what's north of the North Pole. The universe doesn't have a cause, because causation requires time, and time began with the universe. This isn't a dodge. It's not an admission of ignorance. It's a statement about the nature of time itself. This is the orthodox position in cosmology. It's Stephen Hawking's position, derived from his work on black hole thermodynamics and quantum cosmology. In his model, space-time is like the surface of the Earth, finite in extent, but without boundaries or edges. You can traverse the entire surface without ever reaching a point where space ends. Similarly, you can trace back through cosmic time without ever reaching a point before which time doesn't exist. Time becomes spatial near the Big Bang, forming a smooth, closed surface with no singular beginning. It's elegant. It's mathematically consistent, and it completely sidesteps the question by redefining what beginning means. Option 2. Something did come before, but it wasn't time as we know it. Maybe there was a pre-Big Bang universe, a previous cosmic cycle that contracted down to a near singularity and then bounced back out, creating our universe. Maybe the Big Bang was the transition point between contraction and expansion. A cosmic turnaround where the universe changed direction. This is the cyclic model, the eternal return, the cosmic phoenix rising from its own ashes. It's ancient as a philosophical idea. The Greeks and Hindus contemplated eternal recurrence thousands of years ago. but modern physics has given it new mathematical teeth. Roger Penrose proposed conformal cyclic cosmology, where each universe ends in a heat death so complete that all structure disappears, and this structureless state becomes mathematically identical to a new Big Bang. Paul Steinhardt and Neil Turok developed the ekpyrotic universe, where our universe is a three-dimensional membrane floating in higher dimensional space, periodically colliding with other branes and triggering new Big Bangs. These models avoid the singularity. They extend time infinitely into the past. But they introduce new problems. If the universe cycles eternally, why is this cycle? What determines when one cycle ends and another begins? And crucially, do these cycles leave any observable evidence? Can we test them? So far, no one has found a smoking gun. The cosmic microwave background looks the same whether the Big Bang was the beginning or just the most recent bounce. The expansion history, the abundance of elements, the formation of structures, all match the standard Big Bang model regardless of what came before. If there was a previous universe, it's hidden behind an impenetrable veil of cosmic amnesia. Option 3. Our universe is a bubble in an eternally inflating multiverse. This is perhaps the strangest and most mind-bending proposal. It starts with cosmic inflation, a period in the first fraction of a second when the universe expanded exponentially faster than light, driven by a quantum field in an unstable, high-energy state. Inflation solves several problems in standard cosmology: why the universe is so uniform, why it's so flat, why we don't see magnetic monopoles and other exotic relics from the earliest moments. But inflation, once it starts, might never completely stop. The quantum field driving inflation doesn't decay uniformly. Instead, it decays in patches. Each patch becomes a bubble universe, expanding and evolving according to its own physics. But between the patches, inflation continues, spawning more bubbles, which spawn more bubbles forever. The multiverse grows without end, an infinite fractal foam of universes, each with its own Big Bang, its own history, possibly its own physical laws. In this picture, our Big Bang wasn't the beginning of everything. It was just the beginning of our bubble. Time extends infinitely into the past, but that infinite time belongs to the inflating multiverse, not to our particular universe. Before our universe began, there was just more multiverse, more bubbles forming and expanding, an eternal, infinite process with no beginning. It's a seductive idea. It explains why our universe seems fine-tuned for life, not because it was designed, but because we necessarily find ourselves in a bubble where the conditions allow life. All the other bubbles with different physics, where stars can't form or chemistry doesn't work, simply don't have observers to ask why. But it's also deeply troubling. If there are infinite universes with every possible variation of physical laws, then the theory predicts everything and nothing. Every possible observation is realized somewhere. Science, which depends on making testable predictions, seems to lose its footing. How do you test a theory that predicts every outcome? This is the multiverse's philosophical crisis. It might be true. It might be the actual structure of reality, but it might also be fundamentally untestable, forever beyond empirical verification. And if it's untestable, is it even science? Or has physics crossed over into metaphysics, into philosophical speculation dressed up in mathematical language? These are the three major options. Nothing before, because time began. Something before, a previous cosmic cycle. An eternal multiverse, with our universe as just one bubble. Each has its adherents. Each has its problems. None has been proven. None has been ruled out. And this is where you are now, intellectually. Standing at the edge of human knowledge, staring at three equally bizarre possibilities, none of which satisfies your intuition about how things should work, because you want a simple answer. You want someone to tell you, This is what came before. This is how it all started. You want certainty, you want closure, you want the cosmic story to make sense in the same way that everyday stories make sense, with clear beginnings and logical progressions and satisfying conclusions. But the universe doesn't owe you that. Reality isn't obligated to conform to human narrative conventions. The cosmos doesn't care about your psychological need for tidy explanations, and perhaps that's the most profound realization of all. The universe is under no obligation to make sense to you. You're a pattern of matter that emerged within the universe, shaped by evolutionary pressures to survive and reproduce in a narrow range of environments on one small planet. Your brain wasn't optimized to understand quantum gravity or cosmic origins. It was optimized to find food, avoid predators, and navigate social relationships. The fact that you can understand anything about the cosmos is miraculous. 8 billion years ago, that you can write equations describing the curvature of space-time. This is staggering. This is far beyond what evolution should have equipped you for. And yet you've done it. Humanity has done it. A species that spent most of its existence in small hunter-gatherer bands now builds telescopes and particle accelerators and space probes. You've decoded the genome. You've split the atom. You've walked on the moon. You've photographed the surface of Pluto and landed rovers on Mars and sent a probe outside the solar system carrying a golden record with Earth's coordinates and samples of human culture just in case someone's out there listening. You're ridiculous. You're absurd. You're impossible. And you're reaching for the stars anyway. But when you reach for the origin of the universe itself, you're reaching for something that might be forever beyond grasp. Not because you're not smart enough, not because you haven't built the right instruments yet, but because the question itself might be asking for something that doesn't exist. Imagine you're a character in a novel. You become self-aware, curious about your origins. You start investigating the world around you, discovering rules and patterns. You develop a physics of your fictional universe. The answer isn't that you haven't read far enough back in the book. The answer is that there is no before the first page within the context of the story. The story's timeline begins on page 1. Asking what happened before that is asking about the author, the publishing process, the history of literature, things external to the story itself, operating in a completely different framework. Maybe the universe is the same. Maybe asking what came before the Big Bang is asking about something external to physical reality, something that operates in a framework we can't access because we're inside the universe, made of the universe, thinking with structures that are themselves products of the universe's evolution. This is the territory where physics shades into philosophy, where cosmology touches theology, where science reaches its boundary and finds itself staring at questions that might not be scientific questions at all. And yet physicists keep working, keep calculating, keep proposing new theories and searching for ways to test them. Because even if the ultimate question is unanswerable, every step toward it teaches us something new. Every time we push the boundary of knowledge outward, we discover unexpected truths about the universe we do inhabit. The cosmic microwave background was predicted by Big Bang theory decades before it was observed. 7 Kelvin. It wasn't just confirmation of the theory. It was a window into cosmic history, a snapshot of the universe when it was 380,000 years old, a treasure trove of information about the density fluctuations that would eventually grow into galaxies. Gravitational waves were predicted by Einstein's general relativity in 1916. It took 100 years to detect them, and when LIGO finally succeeded in 2015, observing the ripples in space-time from colliding black holes, it opened an entirely new way of observing the universe. We can now listen to the cosmos, hearing the violent collisions of the most extreme objects in existence. Maybe the same will happen with theories of quantum gravity. Maybe someone will make a prediction that seems impossible to test, until a clever experimentalist figures out a way. Maybe we'll find remnants of a pre-Big Bang universe encoded in subtle patterns in the cosmic microwave background. Maybe we'll detect quantum gravitational effects in laboratory experiments, giving us a window into the Planck scale without needing a particle accelerator the size of the galaxy. Or maybe we won't. Maybe some questions are fundamentally beyond empirical investigation. Maybe the origin of time itself is one of them. But here's what makes you human. You ask anyway. You push against the boundary even when you suspect it might be immovable. You stare into the abyss even when it offers no answers. You demand to know where you came from, how you got here, what it all means, even when the universe remains silent. This is the forbidden boundary of knowledge, not forbidden by any external authority, but by the structure of reality itself. The place where time begins, where causation breaks down, where every question dissolves into the fundamental mystery of existence. And you're standing at that boundary right now. You've crossed a threshold. You've moved from the comfortable realm of answered questions into the territory where questions might not have answers. Where physics breaks not because physicists have failed, but because reality itself is stranger than any equation can capture. So what now? Where do you go from here? Forward. Deeper. Into the next section of this journey, where we'll explore exactly how physics breaks at the singularity, where we'll see the mathematical machinery of the universe grinding to a halt, where we'll witness the precise moment when our best theories wave the white flag and admit defeat. BNC is an impossible question. You need to see the impossibility firsthand. You need to watch the equations explode. You need to understand not just that physics breaks, but how and why, and what that means for the nature of reality itself. The universe doesn't owe you answers, but it does offer mysteries. Deep, beautiful, terrifying mysteries that hint at something vast and other beyond the veil of mathematical description. Transforms from a scientific inquiry into a koan, a paradox designed not to be solved, but to shatter your assumptions about what questions even mean. Are you ready? Because once you see how reality breaks at its origin, you can never unsee it. You can never return to the comfortable certainty of simple narratives. You'll carry this knowledge, or rather, this awareness of the limits of knowledge, for the rest of your life. The boundary is approaching. The edge of the knowable universe looms ahead. Physics is about to break in front of your eyes, and you're going to watch it happen. The universe is expanding. 3 words: simple, declarative, factual. You've probably heard them 1,000 times. They appear in textbooks and documentaries and casual conversations about space. They're presented as settled science, a known truth, as uncontroversial as saying water is wet or Earth orbits the sun. But pause for a moment. Actually think about what those words mean. The universe is expanding, not expanding into something, just expanding. All of space, everywhere, getting larger. The distance between galaxies increasing, not because the galaxies are moving through space, but because space itself is stretching, like the surface of a balloon being inflated. Except there is no balloon. There's no surface, there's no outside. The universe isn't embedded in anything. It's not growing into a pre-existing void. Space itself is all there is, and it's becoming more of itself, creating distance where there was less distance before. Your brain struggles with this. It wants to picture the universe as a thing, an object, expanding outward from some central point into empty space beyond. But that picture is wrong. Fundamentally, completely wrong. There is no center. There is no edge. The universe is everything, and everything is getting bigger, and there's nowhere for it to be getting bigger into because where is itself part of what's expanding. This is your first glimpse of how cosmology violates intuition, how the universe operates according to rules that feel impossible, that seem to contradict basic logic, that force you to abandon every spatial metaphor your mind wants to use. And it gets worse. Because if the universe is expanding now, it was smaller in the past. Rewind time, and galaxies that are now billions of light years apart were once closer together. Keep rewinding, and they were touching. Keep going, and all the matter in the observable universe, every atom in every star, every particle in every galaxy, hundreds of billions of galaxies containing hundreds of billions of stars each, was compressed into a region the size of our solar system, then Earth's orbit, then Earth itself, then a city, a building, a room, a grain of sand. Keep going. Smaller than an atom, smaller than a proton, smaller than a quark, down to scales where our understanding of size itself starts to dissolve into quantum uncertainty, down to the Planck length 10 to 35 meters starts 5 meters, where the very concept of distance becomes meaningless, because quantum fluctuations of space-time itself become larger than the distances you're trying to measure. 8 billion years ago, all of existence compressed to a point of such extreme density that physics as we know it simply stops working. Not stops working like a broken machine, but stops working like a fish trying to breathe air. The environment itself becomes incompatible with the rules. This is the singularity, the mathematical knife edge, the moment when our equations produce infinity as an answer. And every physicist knows that infinity in physics isn't a real result. It's a warning sign. It's the universe's way of saying your models don't apply here. But let's not sprint to that boundary just yet. Let's walk there carefully, observing the landscape as we go. Because the journey backward through cosmic time is one of the most extraordinary stories in all of science. It's a story of transformation, of phase transitions, of a universe that was once unrecognizably different from the cold, dark, structured cosmos we inhabit today. Start here, in the present. Look around you. Solid objects, stable matter, clear boundaries between things. You can touch a wall and feel its solidity. You can watch water pour from a glass and see its fluidity. Matter behaves according to predictable rules. Atoms bond into molecules. Molecules organize into structures. Everything has its place. 7 Kelvin above absolute zero, the average temperature of cosmic space, heated only by the faint afterglow of the Big Bang. It's cold, unimaginably cold. Most of the universe is empty vacuum, with occasional islands of matter clustered into galaxies, themselves separated by vast cosmic voids. But it wasn't always cold. It wasn't always empty. 8 billion years, and the universe was a furnace. Not hot like a fire. Not hot like the surface of the sun. Hot in a way that makes stellar interiors look frigid by comparison. In the first second after the Big Bang, the average temperature of the universe was trillions of degrees. Matter as we know it couldn't exist. Atoms couldn't form. Even protons and neutrons, the building blocks of atomic nuclei, were torn apart by the sheer violence of thermal energy. What existed instead was plasma. Not the plasma you might have heard about in physics class, where electrons are stripped from atoms. This was quark-gluon plasma, a state of matter so extreme that even the particles that make up protons dissolve into their constituent quarks and gluons, swimming in a hot, dense soup of fundamental particles. Imagine it. The entire observable universe, all 93 billion light-years of it in our current era, compressed into a volume smaller than our solar system, and that entire volume filled with matter and energy at temperatures that would vaporize anything instantly. No structure, no organization, no chemistry, just raw, undifferentiated energy and matter, identical in every direction, governed only by the fundamental forces of nature at their most basic, symmetric form. This was the universe in its infancy. A cosmic womb. A state of such high energy that the distinctions we take for granted between different types of particles, between different forces, between matter and energy, begin to blur and merge. And this isn't speculation. This isn't philosophical musing. This is extrapolated from observation, derived from multiple independent lines of evidence, confirmed by experiments in particle accelerators, where physicists recreate tiny pockets of this primordial plasma for microseconds before it cools and condenses back into ordinary matter. The evidence is everywhere, written into the structure of the cosmos itself. First, the cosmic microwave background. 8 billion years. It's the oldest light in the universe, released when the cosmos was just 380,000 years old. A snapshot of the infant universe, frozen in time. And that radiation is almost perfectly uniform, almost perfectly smooth. The temperature varies by only 1 part in 100,000 from one region of sky to another. This tells us something profound. The early universe was incredibly homogeneous. Matter and energy were spread out almost evenly, with only tiny fluctuations that would eventually grow under the influence of gravity into the galaxies and clusters we see today. But that uniformity creates a puzzle. Different regions of the cosmic microwave background are so far apart that, according to standard Big Bang theory, they should never have been in contact with each other. Light hasn't had enough time since the Big Bang to travel between them. They're causally disconnected. No information, no influence could have passed between them. So how are they the same temperature? How did they know to be so similar? It's like finding two people on opposite sides of the planet wearing identical, unique outfits, having never met, never communicated, living in complete isolation from each other. The similarity demands an explanation. The answer, or at least the leading candidate, is cosmic inflation, a period in the first fraction of a second when the universe expanded exponentially, faster than light, driven by a quantum field in an unstable, high-energy state. During inflation, a tiny patch of space, smaller than an atom, expanded to cosmic scales in less than 10 to 32 seconds. All the regions we see in the cosmic microwave background came from that single, tiny patch. They started out in contact, reaching thermal equilibrium, and then inflation stretched them apart so rapidly that they became causally disconnected. Inflation solves the uniformity problem, but it introduces new mysteries. What was the inflaton field? What triggered inflation? What ended it? And most disturbingly, if inflation can happen once, why only once? What stops it from happening forever, creating an eternal, infinite multiverse of bubble universes, each with its own Big Bang? Hold that question. We'll return to it. For now, just note how quickly solid explanations in cosmology open doors to deeper mysteries. Second piece of evidence: the abundance of light elements. When physicists calculate what should have formed in the early universe, in those first 3 minutes when temperatures were high enough for nuclear fusion but cool enough for nuclei to survive, they predict specific ratios of hydrogen to helium, to deuterium, to lithium. These predictions depend on the density of matter, the expansion rate, the fundamental physics of nuclear reactions. And when astronomers measure the actual abundances in the oldest, least contaminated regions of space, they find a match. The predictions and observations align with stunning precision. The universe really was a cosmic fusion reactor in its early minutes, forging the lightest elements that would later become the raw material for stars and planets and life. Third, the large-scale structure of the universe. Galaxies aren't randomly distributed through space. They're organized into a cosmic web, filaments and sheets and clusters, connected by tendrils of dark matter, separated by vast voids where almost nothing exists. This structure grew from tiny quantum fluctuations in the early universe, amplified by gravity over billions of years. Computer simulations that start with the conditions predicted by Big Bang cosmology produce structures that look remarkably like what we observe. These three lines of evidence, the cosmic microwave background, light element abundances, large-scale structure, all point to the same conclusion. The universe was once much smaller, much hotter, much denser. The Big Bang model works. It fits the data. It makes predictions that have been confirmed again and again. But here's the unsettling part. It works too well, right up until it doesn't. The physics of the early universe is surprisingly tractable for most of cosmic history. At 1 second after the Big Bang, when the temperature was about 10 billion degrees Kelvin, we can calculate conditions with confidence. Our equations work. Our understanding of particle physics, tested in accelerators here on Earth, applies. We know what particles existed, how they interacted, how they decayed. Go back to 1 microsecond, and the temperature is 1 trillion degrees. Quarks and gluons are still free, not yet bound into protons and neutrons. But we've recreated this state in particle collisions at CERN and Brookhaven. We've measured its properties. We understand it. Even at 10 to 12 seconds, 1 trillionth of a second after the beginning, our physics still applies. The electroweak phase transition happens here, where the electromagnetic and weak nuclear forces, unified at higher energies, separate into distinct forces. We've tested this regime in particle accelerators. The standard model of particle physics describes it accurately, but push back to 10 to 36 seconds, to the end of cosmic inflation. And we're entering territory where our theories become speculative. We have models, but we can't test them directly. The energies involved are far beyond anything we can produce in laboratories. And at 10:43 seconds, the Planck time, the earliest moment where our current physics can even attempt to say anything, we hit a wall. Not a soft boundary, but a hard mathematical singularity where all our equations break down simultaneously. At the Planck time, the universe was at the Planck temperature, 1032 Kelvin. A temperature so high it defies comprehension. The core of the Sun is 15 million degrees. The quark-gluon plasma we create in particle accelerators reaches 1 trillion degrees. The Planck temperature is 100 million trillion degrees. At this temperature, every particle has enough energy to become a black hole. Quantum mechanics and gravity merge into something we don't understand. Space-time itself becomes a foaming, fluctuating quantum entity. This is where physics breaks. This is the edge. And the reason it breaks is mathematically precise. General relativity, Einstein's theory of gravity, describes space-time as a smooth, continuous fabric that curves in the presence of mass and energy. But quantum mechanics describes reality as fundamentally discrete, probabilistic, uncertain at small scales. These two frameworks are incompatible. They make different predictions. They operate according to different rules. For almost everything in the universe, this incompatibility doesn't matter. Gravity dominates at large scales, planets, stars, galaxies. Quantum mechanics dominates at small scales, atoms, particles, forces. The two regimes don't overlap, so we can use each theory in its appropriate domain without worrying about the contradiction. But at the Planck scale, both regimes apply simultaneously. You have quantum effects happening at energies where gravity is strong. You have space-time curvature at scales where quantum uncertainty matters. The two theories collide, and neither one can cope. General relativity predicts that tracing back to the Big Bang leads to a singularity, a point of infinite density, infinite curvature, infinite temperature. But infinity in physics isn't a real answer. Quantum mechanics should step in, smoothing out the singularity with uncertainty and fluctuations. But we don't have a complete quantum theory of gravity to tell us how. String theory offers one possibility. Maybe space-time isn't continuous at the smallest scales. Maybe it's made of tiny, vibrating strings existing in 10 or 11 dimensions. At the Planck scale, these strings and the extra dimensions become important, potentially avoiding the singularity. Loop quantum gravity offers another. Maybe space-time itself is woven from quantum loops, discrete chunks of geometry. Space isn't infinitely divisible. There's a smallest possible volume, a quantum of space. The singularity is replaced by a big bounce, the universe contracting down to the Planck scale and then rebounding outward. Other theories propose even stranger ideas. Emergent gravity suggests spacetime isn't fundamental, but emerges from deeper quantum information. The way temperature emerges from the motion of atoms. Causal set theory treats spacetime as a collection of discrete events connected by causal relationships. Some approaches suggest the universe is a hologram, with all the information about three-dimensional space encoded on a two-dimensional boundary. Each theory is elegant in its own way. Each solves some problems while introducing others. Each makes predictions that are so far impossible to test, and none has achieved consensus in the physics community. This is the state of play. We can trace cosmic history back to the Planck time with some confidence. Before that, we're speculating. We have mathematical frameworks that might apply, but we can't be sure. The earliest moment of the universe remains hidden behind a veil of quantum uncertainty and mathematical incompleteness. Becomes not just difficult, but potentially meaningless, because time itself is part of space-time. It's not an external framework in which the universe exists. It's a dimension of the universe, bound up with space in a four-dimensional manifold. When space-time becomes quantum mechanical at the Planck scale, time becomes quantum mechanical too. It fluctuates. It becomes uncertain. The notion of a clear, well-defined temporal sequence, one moment following another in a definite order, breaks down. This is hard to visualize because your brain evolved to navigate three-dimensional space and one-dimensional time. You experience time as flowing, as having a clear direction from past to future. You remember yesterday, but not tomorrow. You see causes preceding effects. Time feels fundamental, absolute, external to physical processes. But Einstein showed that time is relative. It passes at different rates, depending on your motion and the strength of the gravitational field you're in. A clock on Earth runs slightly slower than a clock on a satellite. An astronaut traveling at high speed ages slower than someone stationary. Time is part of the physical universe, not separate from it. And if time is physical, then at the origin of the universe, where all of physics breaks down, time itself becomes uncertain, quantum, possibly meaningless. Stephen Hawking proposed one solution: imaginary time. In quantum cosmology, you can treat time as a complex number, having both real and imaginary components. Near the Big Bang, time becomes fully imaginary, which mathematically makes it behave like another dimension of space. The universe doesn't have a beginning in time. It has a boundary in four-dimensional space, smooth and finite but unbounded, like the surface of a sphere. In this picture, asking what came before the Big Bang is like asking what's south of the South Pole. The question assumes a geometry that doesn't exist. Time doesn't extend infinitely into the past. It begins at the Big Bang, the way latitude begins at the pole. There's no before because time itself doesn't go beyond that boundary. It's elegant, but it requires accepting that time as we experience it, flowing, directional, absolute, is an approximation, an emergent property that only makes sense far from the Planck epoch. Other physicists reject this. They argue that time must be fundamental, that removing it or making it imaginary is too radical a departure from physical reality. They propose models where time extends infinitely backward, where the Big Bang was a transition rather than a beginning, where our universe emerged from a pre-existing state. The cyclic models fall into this category. Maybe the universe oscillates, expanding and contracting in eternal cycles. Maybe each Big Bang is the rebound from a previous big crunch. Maybe time is truly infinite with no beginning and no end, just an endless series of cosmic cycles. But cyclic models have problems. Each cycle would increase entropy. The universe would become more disordered with each iteration. Eventually, you'd reach a maximally entropic state where nothing interesting could happen. How do you reset entropy between cycles? What mechanism drives the contraction and rebound? And if the cycles are truly eternal, why are we in this particular cycle? The multiverse model sidesteps some of these issues. If inflation is eternal, spawning infinite bubble universes, then time extends infinitely backward. But that time belongs to the inflating multiverse, not to our particular bubble. Our Big Bang was a local event, a bubble nucleating in the larger inflating space-time. Time before our universe was just more multiverse, more bubbles forming, an eternal process with the beginning. This preserves a notion of before, while acknowledging that our universe, our bubble, has a definite beginning within its own timeline. Time for us starts at the Big Bang, but time in the larger multiverse extends infinitely into the past. The philosophical implications are staggering. In an eternally inflating multiverse, everything that can happen does happen somewhere. Every possible variation of physical laws, every possible arrangement of matter, every possible history, all are realized in some bubble universe. Our particular universe, with its particular physics and particular history leading to you reading these words, is just one among infinite possibilities. Becomes a selection effect. The universe appears fine-tuned for life not because it was designed, but because we necessarily find ourselves in a universe where life is possible. All the other universes, where the constants are different, where stars don't form, where chemistry doesn't work, exist too. But they don't have anyone in them asking why. This is the anthropic principle, and it's deeply unsatisfying to many physicists. It turns physics from a search for unique, fundamental explanations into a kind of cosmic environmental biology. Yes, we can explain why our universe has the properties it does, because we couldn't exist in a universe with different properties. But that doesn't feel like a real explanation. It feels like giving up on finding deeper reasons. Yet the multiverse might be real. Inflation predicts it. String theory allows it. Many serious physicists take it seriously. And if it's real, it fundamentally changes what kinds of questions we can answer about cosmic origins. And the answer is other parts of the multiverse, other bubbles, other regions of inflating space-time. The ultimate origin recedes infinitely into the past, forever beyond our reach. This is the cosmic setup, the landscape we're navigating as we try to understand where everything came from. On one side, models where time begins at the Big Bang, where before is meaningless, where the universe is finite in time but unbounded, requiring no external cause. On the other side, models where time extends infinitely backward, where the Big Bang was a local event in a larger cosmological process, where before means something but refers to states we can never observe or verify, and in the middle, the mathematical singularity, the point where all models break down, where physics admits defeat, where our best theories throw up their hands and confess ignorance. What's remarkable is how much we do know, given these fundamental limitations. We can describe the universe accurately from 1 second after the Big Bang forward. We understand the formation of elements, the emergence of structure, the evolution of galaxies. We've detected gravitational waves from colliding black holes. We've imaged the event horizon of a supermassive black hole. We've discovered thousands of exoplanets orbiting distant stars. The success of Big Bang cosmology is extraordinary. The fact that we can peer back through billions of years of cosmic time, reconstruct the conditions of the early universe, and find that our predictions match observations. This is one of the great intellectual achievements of humanity. But that success makes the remaining mystery more acute. We've come so far. We've understood so much. And yet the deepest question, the origin question, the before question, remains stubbornly beyond our grasp. Not because we haven't tried, not because we're not smart enough, but because the question itself might be asking for something that doesn't exist within the framework of physical reality. And this is where the scientific foundation meets the existential vertigo, where the cosmic setup reveals not just what we know, but the shape of what we don't know, where the boundary of knowledge becomes visible, not as a distant horizon, but as a mathematical cliff edge that we've already reached. The early universe wasn't just hot. It was a furnace where time itself was still learning to move, where space was learning to stretch, where the fundamental forces were learning to separate into distinct identities. It was a realm of pure potentiality, where everything that would become our familiar, structured cosmos existed only as quantum fluctuations in a roiling sea of energy. And before that? Before the furnace was lit? Before time began its flow? Before space stretched into existence? That's not a scientific question with a scientific answer. That's a question that points beyond science, into territory where mathematics and philosophy, and even theology, brush against each other awkwardly, none quite adequate to the task of explanation. But here's the thing. That inadequacy isn't a failure. It's a feature. It's the universe telling us something profound about the nature of existence itself. Not everything has an explanation. Not everything needs a cause. Not everything can be traced back to something prior. This is the brute fact of existence. Reality exists. The universe is. And any explanation for why it exists would itself require an explanation. And that explanation would require another, in an infinite regress that never reaches solid ground. At some point, you have to accept that the chain of explanations ends, that there's a foundation that has no foundation beneath it, that existence is, in some sense, self-explanatory or inexplicable. And maybe those two things are the same. The early universe was a place of transformation, of phase transitions, of symmetry breaking. It was a place where the forces of nature, unified at high energies, separated into the distinct forces we know: gravity, electromagnetism, the strong and weak nuclear forces. This separation wasn't arbitrary. It was driven by the universe's expansion, by the cooling that comes with expansion. As temperature dropped, energy decreased, and the symmetric, unified state became unstable. Like water freezing into ice, the universe underwent transitions that broke the original symmetry, creating the diverse, structured cosmos we inhabit. But the original symmetric state, the unified state at the highest energies, that might be the closest thing to a fundamental description of reality, not emptiness, not nothingness, but pure, symmetric, undifferentiated potentiality. And the answer might be a state of perfect symmetry containing all possibilities, none yet realized. A quantum vacuum, seething with virtual particles and fluctuating fields, a mathematical structure, abstract and timeless, from which physical reality emerges. These ideas sound mystical. They sound like philosophy dressed in physics terminology, but they're grounded in serious mathematical frameworks, in theories that physicists have spent decades developing. The universe has no edge. Everywhere you go, you find more universe, more space, more galaxies, stretching on in every direction. If you could somehow travel faster than the expansion and keep going forever, you'd never reach a boundary. So where does it begin? If there's no edge in space, how can there be an edge in time? How can the universe have a beginning when it has no boundaries? This is the contradiction at the heart of cosmology, 8 billion years ago when everything started. But the logic of a universe without edges suggests that beginnings and endings are spatial concepts that don't apply to the cosmos as a whole. The resolution might be that time itself is bounded but not edged. Like the surface of a sphere, the timeline of the universe might be finite in extent, but without any boundaries. You can traverse the entire surface of Earth without ever reaching an edge. Or maybe time is infinite, and the Big Bang was just a local event, a transition from one phase to another in an eternal cosmos. Or maybe time doesn't exist at the most fundamental level, and the flow we experience is an emergent phenomenon, like the way temperature emerges from molecular motion. These aren't settled questions. They're active areas of research with physicists arguing passionately for different positions, developing competing theories, searching for ways to test ideas that might seem untestable. And that's where we are now, standing in the cosmic setup, understanding that the universe was once unimaginably different. Knowing that the trail of evidence leads back to a moment of extreme heat and density. Recognizing that our physics works extraordinarily well up to a point and then breaks down completely. The stage is set, the foundation is established. You know now that the early universe was a seething plasma, that it expanded and cooled, that it underwent transformations that shaped everything we see today. You know that the Big Bang model is successful but incomplete. You know that the question of origins remains open, contested, possibly unanswerable. Now comes the descent, the journey into the heart of the singularity, where mathematics itself begins to scream in protest, where infinity appears in equations like a wound in reality, where every certainty dissolves into quantum foam. You're about to see exactly how physics breaks at the boundary of time. Isn't just a difficult question. It's a question that might be asking about something that doesn't exist. There's a moment in every physicist's education when they first encounter the singularity, not as an abstract concept, not as a word in a textbook, but as an actual mathematical result staring back at them from their own calculations. They're working through the field equations of general relativity, tracing the path of space-time curvature backward in time, and suddenly the numbers start behaving strangely. Densities increase without bound. Curvatures approach infinity. The mathematical machinery that has been humming along smoothly suddenly seizes up, grinds to a halt, and produces results that make no physical sense. That moment is revelatory. It's when you realize that the universe isn't just playing by rules we haven't discovered yet. It's when you suspect that at the origin of everything, the rules themselves might dissolve into something we can barely conceptualize, let alone calculate. The singularity isn't a place. This is the first thing you need to understand. When physicists talk about the Big Bang singularity, they're not describing a point in space where everything was located. They're describing a condition where space-time itself becomes infinitely curved, where the fabric of reality develops what mathematicians call a pathological feature, a place where the equations break down and lose all predictive power. Imagine you're driving along a road, following a GPS that gives you perfect directions. Every turn is precisely calculated. Every distance is accurate. You trust it completely because it's never been wrong. Then suddenly, without warning, the GPS screen glitches. The map dissolves into static. The distance readout starts flashing random numbers. The heading indicator spins wildly. The device hasn't just lost signal. It's encountered a situation for which it has no programming, no framework, no way to process what's happening. That's what happens to general relativity at the singularity. The theory hasn't just reached the limit of its accuracy. It's encountered a situation for which its mathematical structure provides no meaningful answers. And unlike a GPS that can wait for signal to return, general relativity can't move past this point. The singularity is, in mathematical terms, the end of the road. Albert Einstein published his field equations of general relativity in 1915, a set of 10 interlinked differential equations that describe how matter and energy curve space-time, and how that curvature influences the motion of matter and energy. They're beautiful equations, elegant in their geometric simplicity, revolutionary in their implications. They replaced Newton's instantaneous gravitational force with something far stranger: the idea that mass and energy warp the fabric of space and time itself, and objects move along the straightest possible paths through this warped geometry. But Einstein's equations have solutions that Einstein himself found troubling. In 1916, Karl Schwarzschild discovered an exact solution describing the spacetime around a spherically symmetric mass. This solution predicted something bizarre. If you compressed enough mass into a small enough volume, spacetime would curve so severely that nothing, not even light, could escape from within a certain radius. The escape velocity would exceed the speed of light. This was the first mathematical description of what we now call a black hole. And at the center of a Schwarzschild black hole, the equations predict a singularity, a point where density becomes infinite, where space-time curvature becomes infinite, where the mathematical description breaks down completely. Einstein didn't like this. He thought singularities were artifacts of idealized mathematical models, not features of physical reality. He believed that realistic situations, with rotation, with asymmetries, with quantum effects, would avoid the singularity somehow. He was wrong. In the 1960s, Roger Penrose and Stephen Hawking proved a series of theorems showing that singularities are generic features of general relativity, not mathematical curiosities. Under very general conditions, conditions that are satisfied in the real universe, space-time must develop singularities. Black holes must have singularities at their centers. And if you run the cosmic expansion backward in time, the entire universe must have emerged from a singularity. These weren't approximations or special cases. These were rigorous mathematical proofs. The Penrose-Hawking singularity theorems demonstrated that general relativity, taken seriously, predicts its own breakdown. The theory contains within itself the seeds of its own incompleteness. This is conceptually jarring. Imagine discovering that the rules of chess, applied consistently, inevitably lead to a position on the board that the rules can't handle. A configuration where the very concept of legal move becomes undefined. That's what the singularity theorems revealed about general relativity and the structure of spacetime. But what does a singularity actually mean physically? What happens there? The honest answer is, we don't know. The mathematical singularity might correspond to a physical singularity, a genuine point of infinite density and curvature, or it might be an artifact of using a theory beyond its domain of validity, like using classical mechanics to describe electrons in atoms. The classical description produces nonsense, but the quantum description works perfectly. Maybe the same is true here. Maybe quantum effects smooth out the singularity, replacing it with something strange, but finite. This is where quantum mechanics enters the story. And this is where things get truly complex, because quantum mechanics and general relativity are fundamentally incompatible frameworks. Quantum mechanics is probabilistic. It describes reality in terms of wave functions that evolve deterministically according to the Schrödinger equation. But when you make a measurement, you get a random outcome drawn from a probability distribution. Position, momentum, energy. These aren't definite values until you measure them. Until then, particles exist in superpositions, simultaneously occupying multiple states. Quantum mechanics is discrete. Energy comes in packets called quanta. Angular momentum is quantized. Even the process of measurement is fundamentally discontinuous. The wave function collapses from a smooth superposition to a definite state instantaneously. Quantum mechanics is non-local. Particles can be entangled, sharing correlations that persist across arbitrary distances, correlations that violate the classical intuition that information can't travel faster than light. Einstein called this spooky action at a distance and never fully accepted it, but experiment after experiment has confirmed it. General relativity, by contrast, is deterministic. The Einstein field equations tell you precisely how space-time will evolve, given initial conditions. There's no randomness, no probability, no collapse. General relativity is continuous. Space-time is smooth, differentiable, described by continuous functions. The geometry changes smoothly from point to point. General relativity is local. The curvature of space-time at any point depends only on the matter and energy at that point and in its immediate neighborhood. Influences propagate at the speed of light, no faster. These aren't just different approaches or mathematical conveniences, they're incompatible worldviews, and both are confirmed by experiment to extraordinary precision in their respective domains. Quantum mechanics has been tested to 1 part in a trillion. General relativity has been confirmed in systems ranging from GPS satellites to gravitational wave detections from colliding black holes. But when you try to merge them, when you try to describe gravity quantum mechanically or space-time quantum mechanically, everything breaks. The standard approach to making a theory quantum mechanical is called canonical quantization. You take the classical theory, identify the position and momentum variables, and promote them to operators that satisfy specific commutation relations. This works brilliantly for electromagnetism, producing quantum electrodynamics, the most precisely confirmed theory in all of physics. But when you try to apply this approach to general relativity, you run into immediate problems. In general relativity, space-time itself is dynamical. It's not a fixed background stage on which events occur. It's part of the physics, something that evolves and changes. So what do you quantize? Space? Time? The metric that measures distances? When you try, you get equations that are incredibly complex, that have no known solutions, that produce infinities in calculations that should yield finite answers. The mathematics becomes intractable. The physical interpretation becomes unclear. After decades of effort by brilliant physicists, there's still no complete, consistent quantum theory of gravity derived by quantizing general relativity. This failure isn't just technical. It might be telling us something profound about the nature of space-time itself. Maybe space-time isn't fundamental. Maybe it emerges from something deeper, something that's inherently quantum mechanical but doesn't look like space-time at small scales. This is the territory where modern approaches to quantum gravity live. String theory, loop quantum gravity, causal dynamical triangulations, asymptotic safety, emergent gravity. Each proposes a radically different picture of what space-time really is at the most fundamental level. String theory says that particles aren't point-like objects, but tiny, vibrating strings. These strings exist in 10 or 11 dimensions, the 3 spatial dimensions we experience, plus time, plus 6 or 7 additional dimensions that are curled up, compactified, too small to observe directly. The different vibrational modes of the strings correspond to different particles. One mode is an electron, another is a quark, another is a photon, and one particular mode is a graviton, the particle that mediates gravitational force. In string theory, the catastrophic infinities that plague quantum gravity are tamed by the extended nature of strings. Point particles can get arbitrarily close to each other, producing infinite interaction energies. But strings have finite size, a minimum length scale, and this automatically cuts off the infinities. The theory is mathematically consistent, at least in principle. It unifies all forces and particles in a single framework. But string theory has problems. It doesn't make unique predictions. There are something like 10 of 500 possible ways to compactify the extra dimensions, each giving rise to a different effective physics in our four-dimensional world. This is called the string landscape, and it's so vast that almost any physics you might imagine appears somewhere in it. How do we determine which compactification describes our universe? String theory doesn't tell us. Moreover, string theory is formulated in a flat, fixed space-time background. It describes strings moving through space, but space itself isn't emergent or dynamical in the way general relativity requires. There are versions of string theory, M-theory, matrix theory, that attempt to address this, but they're even less well-developed, even more speculative. And crucially, string theory has made almost no testable predictions. The energy scales where stringy effects become important are so far beyond current experiments that we can't directly confirm or refute the theory. Some physicists argue this makes it philosophy rather than physics. String theorists respond that the mathematical consistency and elegance of the theory are evidence enough, and that technological limitations shouldn't disqualify a theory that might be true. Loop quantum gravity takes a different approach. Instead of adding extra dimensions or new fundamental objects, it attempts to quantize space-time itself directly. Space, in this picture, isn't continuous. It's woven from quantum threads, loops of gravitational field lines that form a discrete network. The geometry of space is built up from these elementary loops, the way fabric is woven from threads. In loop quantum gravity, there's a smallest possible volume, roughly the Planck volume, 10^105 cubic meters, and a smallest possible area, roughly the Planck area, 10 or 70 square meters. You can't subdivide space beyond these scales. Space is fundamentally granular, discrete, quantized. This discreteness has dramatic implications for the Big Bang singularity. In classical general relativity, you can trace backward in time to smaller and smaller volumes without limit, eventually reaching a point of zero volume and infinite density. But in loop quantum gravity, there's a minimum volume. The contraction stops when the universe reaches the Planck scale. What happens then? The universe bounces. The contraction reverses into expansion. The Big Bang wasn't a singular beginning, but a transition point, a quantum bounce from a contracting phase to an expanding phase. Before the Big Bang was another universe, contracting under gravity, until it reached the minimum volume allowed by quantum geometry, then rebounding outward. This is called the Big Bounce, and it's one of the most elegant solutions to the singularity problem. It avoids the mathematical infinities. It makes the Big Bang comprehensible as a physical process rather than a metaphysical mystery. But loop quantum gravity has its own issues. The theory is background independent. It doesn't assume a pre-existing space-time, but this makes it incredibly difficult to calculate anything. Most of the important results exist only in simplified models, like mini-superspaces or symmetry-reduced versions of the full theory. Whether the complete theory actually works, whether it successfully describes all of physics, remains an open question. And like string theory, loop quantum gravity hasn't made clear, testable predictions that would allow us to distinguish it from competitors. There are proposals to look for signatures in the cosmic microwave background, subtle statistical patterns that might reveal quantum gravitational effects from the bounce. But so far, nothing definitive has emerged. So we have two major candidates for quantum gravity, neither complete, neither tested, neither clearly correct. And they represent fundamentally different visions of what space-time is. String theory keeps space-time continuous, but adds dimensions and new fundamental objects. Loop quantum gravity makes space-time discrete but avoids extra dimensions and exotic entities. Both could be wrong. One could be right. Or they might be different approximations to some deeper, more comprehensive theory we haven't discovered yet. This is the state of fundamental physics at the edge of the knowable. We know our current theories are incomplete. We know that a quantum theory of gravity must exist because quantum mechanics and gravity both exist. But we don't know what that theory looks like. We don't know if space-time is fundamental or emergent, continuous or discrete, four-dimensional or higher dimensional. And this uncertainty isn't just about academic details. It's about the most basic question you can ask about the universe. What is it made of? What is the fundamental substrate of reality? Because if space-time is emergent, if it arises from something more primitive, then asking what came before the Big Bang might be asking the wrong question entirely. It might be like asking what flavor the color blue is, or what temperature justice has. A category error, applying concepts from one domain to another where they don't apply. Imagine reality as a film reel. Each frame is a three-dimensional snapshot of the entire universe at a particular moment in time. The frames are stacked in sequence, and as you move through the stack, you experience the flow of time. Events unfold, causes lead to effects. History progresses. This is called the block universe, and it's one way of thinking about time in relativity. According to special relativity, the division of space-time into space at a particular time is observer-dependent. Different observers moving at different velocities will disagree about which events are simultaneous. There's no absolute universal now that everyone agrees on. This suggests that all moments in time are equally real. The past didn't cease to exist when it became past. The future doesn't come into existence as it becomes present. All of space-time, all events, past, present, and future, exists as a single four-dimensional block. Time doesn't flow. We move through it, or our consciousness does, experiencing one moment after another, but the moments themselves are all there, laid out in the eternal structure of space-time. In this picture, the Big Bang is just the edge of the film reel, the first frame. You can ask what's on the frame, what's depicted in that earliest moment. The reel has a finite length, a definite beginning, but it's not embedded in some larger timeline. It's the complete timeline, all of it, from beginning to end. This is a powerful and unsettling idea. It means that your entire life, every decision, every moment of joy or sorrow, every breath you'll ever take, already exists, in some sense laid out in the four-dimensional structure of space-time. The future is already there, just as real as the past, even though you haven't experienced it yet. It means that change is an illusion. The universe isn't changing, isn't evolving. It simply is, a static geometric object in four dimensions. What changes is your position along your world line, your trajectory through space-time. You're moving through the block, experiencing different moments in sequence, but the moments themselves are fixed, eternal, unchanging. Does this mean the future is predetermined? That free will is impossible? Not necessarily. The block universe describes what happens, not why it happens, or whether it could have happened differently. You might still have genuine choices, even if those choices are already part of the four-dimensional structure. The compatibilist philosopher would say that free will is about your decisions being caused by your own reasoning and desires, not about whether the future is open or closed. But it does mean that the flow of time, that sense you have of moving from past through present toward future, is not a fundamental feature of reality. It's something that emerges from your perspective as a conscious being embedded in space-time, experiencing moments sequentially, unable to perceive the entire four-dimensional structure at once. Becomes even stranger, because the question assumes a temporal flow extending beyond the Big Bang. But if time is just another dimension of the block, then the Big Bang is simply the boundary of that dimension. There's no outside to ask about. Yet the block universe picture has its critics. Many physicists, particularly those working on quantum gravity, argue that time must be more fundamental than space, that there's something special about temporal evolution, about causality, about the distinction between past and future. In quantum mechanics, time plays a unique role. It's a parameter, not an observable. You can measure position, momentum, energy, but you can't measure time in the same way. Time is the background against which quantum evolution occurs, the parameter in the Schrödinger equation that tells you how the wave function changes. Some approaches to quantum gravity, like causal set theory, take this seriously. They propose that causality, the relation of before and after, the structure of cause and effect, is more fundamental than space-time geometry. Space-time emerges from a network of causal relationships, a partial ordering of events where some events are in the causal past of others, some in the causal future, and some are causally disconnected. In this picture, asking what came before the Big Bang is asking whether there are events in the causal past of the Big Bang. And the answer might be no. The Big Bang might be the earliest event, with nothing in its causal past. Or the answer might be yes. There might be a previous cosmological phase, a pre-Big Bang universe, causally connected to ours through the bounce or transition. It's asking about causal structure, not temporal flow. And causal structure might extend beyond the classical notion of time. There might be causal relations without a well-defined time coordinate, especially in quantum gravitational regimes where space-time itself is fluctuating and uncertain. This brings us to one of the most radical ideas in modern physics, the emergence of time. What if time isn't fundamental at all? What if the flow of time, the directionality from past to future, the entire experience of temporal passage, what if all of this emerges from something deeper, something that doesn't have a time dimension? This sounds absurd. How can time emerge? Time is the most basic aspect of experience. You can't imagine existence without time. Even the word emerge implies a temporal process, something coming into being over time. How can time itself emerge? Yet there are theoretical frameworks where exactly this happens. In some versions of string theory, space-time emerges from a quantum state of strings and branes, a state that exists in some abstract configuration space without any temporal structure. In some interpretations of quantum mechanics, time emerges from the way subsystems of the universe become entangled with each other. In certain approaches to quantum gravity, time is an approximate concept that only makes sense in low-energy, large-scale limits. Carlo Rovelli, one of the founders of loop quantum gravity, has argued extensively that time is not fundamental. At the most basic level, he suggests, there's no global time variable, no universal clock ticking away. There are only events and causal relationships between events. What we call time is a coarse graining, a statistical approximation that emerges when you look at large numbers of degrees of freedom collectively. Think about temperature. At the fundamental level, there's no such thing as temperature. There are only molecules moving with various velocities. Temperature is a statistical concept, an average over many molecules, a macroscopic property that emerges from microscopic dynamics. You can't point to a single molecule and ask for its temperature. The question doesn't make sense at that scale. Maybe time is the same. At the Planck scale, at the level of quantum geometry, there might be no time variable, just quantum states, evolving according to timeless quantum equations, entangling with each other in complex ways. And from this entanglement, from the way different regions of the quantum state become correlated, something resembling time emerges at larger scales. In this picture, the Big Bang isn't the beginning of time. It's a boundary in the emergent time variable, a place where the approximation breaks down, where the statistical description no longer applies. Asking what came before is like asking what the temperature was before there were enough molecules to define temperature. The question presupposes a framework that doesn't exist at that level. This is deeply strange, but it has a kind of logical elegance. If time is emergent, then the paradoxes of the Big Bang dissolve. There's no infinite past to explain. There's no temporal causation to worry about. There's just a fundamental quantum state, possibly eternal and unchanging in some abstract sense, from which our universe, with its apparent temporal flow, emerges. But how do you test this? How do you determine whether time is fundamental or emergent? These questions push against the boundaries of empirical science. We can't directly observe the Planck scale. We can't run experiments on the quantum structure of space-time. We're left with mathematical consistency, with aesthetic criteria, with hoping that the right theory will make predictions, subtle, indirect, but testable predictions, that will allow us to distinguish it from alternatives. Some physicists propose looking at quantum superpositions of space-time geometries. If space-time is quantum mechanical, then it should be able to exist in superpositions, just like particles can be in superpositions of position or momentum. Maybe there are situations, exotic particle interactions, extreme gravitational fields, precision measurements of quantum systems, where we could detect the signature of space-time superposition. Others suggest that quantum gravity might leave imprints in the cosmic microwave background. The inflationary epoch occurred at energies where quantum gravitational effects might have been important. These effects might have seeded the initial density fluctuations in a characteristic way, leaving a pattern we could detect with sufficiently precise observations. Still others look to black hole physics. Black holes are laboratories for quantum gravity. At the event horizon, and especially at the singularity, quantum effects and gravitational effects become comparable in strength. Studying how black holes evaporate through Hawking radiation, how information escapes from black holes, might give us clues about the quantum structure of spacetime. These are subtle, difficult, indirect tests, but they're not impossible. Science has overcome similar challenges before. When quarks were first proposed, many physicists thought they were just mathematical conveniences, not real particles, because you can never isolate a quark. They're always confined inside protons and neutrons. But clever experiments looking at scattering patterns and bound states eventually confirmed that quarks are real, even if we can't see them individually. Maybe the same will happen with quantum gravity. Maybe someone will devise a clever experiment, an indirect probe, a way to test these ideas that seems impossible right now but will become feasible with new technology or new insights. Or maybe not. Maybe quantum gravity is genuinely beyond the reach of experiment. Maybe the energies required are so extreme, the effects so tiny, that no technological advance will ever let us test these theories directly. That would be frustrating, even tragic. Science depends on the interplay between theory and experiment. Theory proposes, experiment disposes. Without experiments to test them, theories become untethered from reality, free to multiply without constraint. How do you choose between them? Mathematical consistency helps, but it's not enough. Many mathematically consistent theories describe worlds nothing like ours. This is the crisis some physicists see looming in fundamental physics. The gap between our highest energy experiments, the Large Hadron Collider, probing energies around a few trillion electron volts, and the Planck energy, where quantum gravitational effects become strong, is enormous. The Planck energy is about 10⁻19 times higher than what the LHC can reach. Building an accelerator to reach Planck energies would require a ring the size of the Milky Way galaxy. Barring some unexpected breakthrough, some new window into high-energy physics, we might be stuck with theories we can develop mathematically, but never confirm empirically. And that raises uncomfortable questions about whether these theories are really science or whether they've crossed over into sophisticated mathematical philosophy. Yet the universe exists. Quantum mechanics and gravity both exist. They must be unified somehow. The quantum theory of gravity is out there, embedded in the structure of reality, whether we can fully discover it or not. And even if we can't test it directly, even if we can't build experiments at the Planck scale, the theory must still be consistent with everything we can observe at lower energies. This provides constraints. The quantum theory of gravity must reduce to general relativity in the classical limit. It must reduce to quantum field theory in the low energy limit. It must explain the observed properties of our universe, why space is three-dimensional or appears three-dimensional, why the cosmological constant has the value it does, why the fundamental forces have their observed strengths. These requirements, stringent as they are, still leave enormous freedom. Many theories satisfy these basic constraints. How do we narrow the field? Some physicists appeal to elegance, simplicity, mathematical beauty. The right theory should be aesthetically pleasing, simple in its principles, even if complex in its implications. This is how Einstein thought. He trusted his geometric intuition, his sense of mathematical beauty, and it guided him to general relativity. But beauty is subjective. What one physicist finds elegant, another finds contrived. String theory's unification of all forces and particles is beautiful to some, but its 10,500 possible vacua strike others as hopelessly complicated. Loop quantum gravity's background independence is elegant to some, but its mathematical intractability bothers others. There's no royal road here, no clear path to the truth, just hard work, mathematical exploration, and the hope that eventually, somehow, nature will provide a clue, a subtle signal in the data, an unexpected phenomenon, a pattern that points toward the right theory. Now let's turn to something even more mind-bending, the possibility that our universe is one bubble in an infinite multiverse, and that the Big Bang wasn't a unique event, but one of countless similar events occurring eternally in a vast inflationary space-time. Cosmic inflation was proposed in the 1980s by Alan Guth, Andre Linde, and others to solve several problems in standard Big Bang cosmology. Why is the universe so uniform, with almost identical properties in regions that were never in causal contact? Why is space so close to flat, neither curved like a sphere, nor curved like a saddle? Why don't we observe magnetic monopoles and other exotic particles that should have formed in the early universe? Inflation answers all these questions. In the first fraction of a second, a quantum field, the inflaton field, was in an unstable, high-energy state. This state acted like a cosmological constant, driving exponential expansion. In less than 10^32 seconds, the universe expanded by a factor of at least 10^26, possibly much more. This rapid expansion smoothed out any initial irregularities, making the universe uniform. It stretched space so flat that any initial curvature became negligible, and it diluted exotic particles to such low densities that we'd never expect to see one. After this brief inflationary period, the inflaton field decayed into ordinary particles, reheating the universe and beginning the standard hot Big Bang evolution. Inflation doesn't replace the Big Bang, it precedes it, setting up the initial conditions that make the standard cosmology work. Evidence for inflation has been accumulating for decades. The pattern of fluctuations in the cosmic microwave background matches inflation's predictions remarkably well. The statistical properties of galaxy distributions match what inflation predicts. Every new observation seems to confirm the basic picture. But inflation has a strange property. Once it starts, it's hard to stop completely. The inflaton field doesn't decay uniformly everywhere. Quantum fluctuations cause it to decay in some regions while continuing to inflate in others. Each decaying region becomes a bubble universe, expanding and evolving according to its own physics. But the regions that don't decay keep inflating, growing exponentially, spawning more bubbles. This is eternal inflation. Once inflation begins anywhere, it produces infinite volume exponentially fast, and that infinite volume contains infinite bubble universes, each potentially with different properties. Our observable universe is just one bubble, one tiny region where inflation ended and normal cosmic evolution began. In eternal inflation, the multiverse has no beginning. Inflation is eternal into the future. There will always be regions still inflating, always spawning new bubbles. But is it eternal into the past? Did inflation itself have a beginning? This question sparked a major debate in the early 2000s. Arvind Borde, Alan Guth, and Alexander Vilenkin proved a theorem showing that any universe that's been expanding on average must have a boundary in the past. You can't have eternal inflation extending infinitely into the past if space is always expanding. There must have been a beginning, a point where inflation started. But other physicists pointed out loopholes. Maybe the universe contracts and then bounces into inflation. Maybe it undergoes cycles. Maybe there are quantum gravitational effects that allow the universe to tunnel from nothing into an inflating state. The theorem rules out simple eternal expansion into the past, but it doesn't rule out all possibilities for avoiding a beginning. The question remains open. But if eternal inflation is true, then even if the inflating multiverse had a beginning, that beginning is fundamentally different from our Big Bang. Our Big Bang is a local event, the end of inflation in our particular bubble. The true beginning, if there was one, would be the start of inflation itself, the moment when the inflaton field first reached its high-energy state. What could cause that? How does inflation begin? Some proposals invoke quantum tunneling. In quantum mechanics, systems can tunnel from one state to another even if they don't have enough energy to get there classically. An electron can tunnel through a potential barrier. A radioactive nucleus can tunnel into a lower energy state, emitting radiation. Maybe the universe tunneled from nothing, or from some pre-inflationary state, into an inflating state. Alexander Vilenkin developed this idea in his universe from nothing proposal. In quantum cosmology, you can write down a wave function for the entire universe, describing the probability amplitude for different geometries and field configurations. Vilenkin showed that this wave function includes contributions where the universe tunnels from a state of zero size, literally nothing, into a tiny, inflating bubble. This is conceptually startling. The universe doesn't need a cause. It can simply quantum tunnel into existence, emerging from the quantum foam of virtual geometries, growing from a Planck-scale fluctuation into a vast inflating cosmos. But this raises immediate questions. If the universe can tunnel from nothing, why does it tunnel into an inflating state specifically? Why not some other configuration? And what does nothing mean here? Is it really nothing, or is it a quantum vacuum with its own physics, its own laws, its own structure? Stephen Hawking and James Hartle proposed an alternative, the no-boundary proposal. Instead of the universe tunneling from nothing, they suggest that the universe is self-contained, finite in time but without a boundary or edge. Near the Big Bang, time becomes space-like, and the universe's history forms a closed surface, like the surface of a sphere. In this picture, asking what came before the Big Bang is like asking what's south of the South Pole. The question assumes a geometry that doesn't exist. Time doesn't extend infinitely into the past. It's finite. Like the distance from equator to pole is finite. But there's no boundary, no edge, no beginning in the sense of a first moment preceded by nothing. This is elegant, but it requires accepting that time is not fundamental, that it can smoothly transition into space, that our intuitive notion of temporal flow breaks down at the Planck scale. And like many ideas in quantum cosmology, it's extremely difficult to test. Then there are cyclic models, where our Big Bang was the rebound from a previous big crunch. The universe undergoes infinite cycles of expansion and contraction. Each cycle ends when gravity overcomes expansion and the universe contracts back down. But instead of collapsing to a singularity, quantum effects cause a bounce, and the universe rebounds into a new cycle of expansion. Roger Penrose's conformal cyclic cosmology, CCC, proposes a variant. Each cycle begins with a Big Bang and ends with a universe so expanded, so diluted, that all structure has disappeared. In this far future state, with no particles with mass, no way to measure time or distance, the geometry becomes conformally equivalent to a new Big Bang. The end of one cycle becomes the beginning of the next. Penrose claims to have found evidence for this in the cosmic microwave background, circular patterns that might be signatures of colliding black holes from the previous cycle. Other cosmologists are skeptical, arguing that the patterns could be statistical flukes or artifacts of data analysis. Paul Steinhardt and Neil Turok's ekperiodic universe takes yet another approach. Our universe is a three-dimensional membrane, a brain, floating in a higher dimensional space. There are other brains nearby. Periodically, these brains collide. Each collision triggers a Big Bang on both brains, creating two new universes. Between collisions, the brains separate and evolve, then eventually collide again. These cyclic models avoid the singularity by replacing it with a bounce or transition. They preserve a notion of before by extending time infinitely into the past. But they face challenges. Entropy increases with each cycle. Where does it go? How is it reset? And how do you test these models? Do the cycles leave observable traces? Each approach, eternal inflation, quantum tunneling, no boundary proposal, cyclic models, offers a different resolution to the question of cosmic origins. Each is mathematically sophisticated, developed by world-class physicists, grounded in serious theoretical work. And each is, so far, unproven and possibly untestable. This is the landscape of modern cosmology, a plethora of ideas, a dearth of decisive evidence. We're in the realm where mathematics and imagination intersect, where the constraints are logical consistency and compatibility with known physics, where the final arbiter, experiment, remains frustratingly out of reach. And lurking behind all these proposals is a deeper question. Why is there something rather than nothing? This is philosophy's oldest question, and physics hasn't answered it. Even if we explain how the universe began, through quantum tunneling, or eternal inflation, or a bounce from a previous cycle, we're left asking, why those laws? Why quantum mechanics? Why does anything exist at all? Some physicists argue this question is beyond science. Science explains phenomena in terms of laws and initial conditions. But the existence of laws themselves, the brute fact that reality operates according to rules, rather than being pure chaos or pure nothingness, that seems to require explanation outside of science, in metaphysics or theology, or some framework beyond empirical investigation. Others argue that existence is necessary, that perhaps only one consistent set of mathematical structures can exist, and physical reality is that structure manifesting, that nothingness is impossible, incoherent, that something must exist because non-existence is self-contradictory. This is the territory of Max Tegmark's mathematical universe. Hypothesis. Tegmark proposes that physical reality is a mathematical structure, and all mathematical structures that are consistent and sufficiently complex exist as physical realities. Our universe is one such structure. Spinsox has a simple answer, because mathematical structures exist necessarily by virtue of being logically consistent. Has an anthropic answer, because we necessarily find ourselves in a universe with properties that allow observers to exist. It's a radical form of Platonism, the idea that mathematical objects are more real than physical objects, that physics is applied mathematics, that discovering physical laws is the same as discovering mathematical truths. Many physicists find this too abstract, too untethered from physical reality, but it has a strange appeal. It makes existence necessary rather than contingent. It answers the deepest why question by dissolving it. Things exist because they must, because existence is a property of mathematical consistency, and it has an unexpected consequence. If all mathematical structures exist, then there's no ultimate origin question. The multiverse of all mathematical structures doesn't come from anywhere. It doesn't begin. It simply is, eternally and necessarily outside of time, beyond causation, existing in the Platonic realm of abstract mathematical truth. This brings us full circle. We started with the singularity, the point where physics breaks down. We've explored quantum gravity, emergent time, eternal inflation, cyclic cosmologies, quantum creation. Nothing came before because the question itself is malformed, applying temporal concepts where they don't belong. Time might begin at the Big Bang, or it might extend infinitely into the past through cycles or eternal inflation, or it might be emergent, not fundamental, an approximation that breaks down at the Planck scale, or it might be part of a higher dimensional structure where our notion of temporal sequence is just one slice through a more complex reality. We don't know. We're honest about not knowing. And that honesty, that admission of ignorance, is itself a profound statement about the limits of human knowledge and the structure of reality. But let's go deeper still. Let's examine the specific paradoxes that emerge when you try to think clearly about the origin of time. Let's see exactly how causation breaks, how infinity haunts every attempt at explanation, how every answer generates new questions. Because the mystery isn't just that we don't know what came before. The mystery is that the question itself might be revealing fundamental limits on what any intelligence, human or otherwise, could ever know about the nature of existence. You've been holding your breath without realizing it. Not literally, perhaps, but intellectually, emotionally. You've been following equations and theories and mathematical abstractions, treating them like puzzles to solve, problems to understand. You've maintained that comfortable distance between yourself and the implications, between the cosmic story and your story. But now that distance collapses. Because everything we've discussed, the singularity, the breakdown of time, the possibility that before is meaningless, isn't just about the universe out there. It's about you, here, now, reading these words, existing in this moment. If time began at the Big Bang, then there was no duration before you existed. 8 billion years is a finite stretch. Before that, nothing, not darkness, not waiting, not potential, nothing. And that means that your existence, this moment of consciousness, this experience of being you, emerged from that nothing. There was a state of reality where you not only didn't exist, but where the very concept of existence, the framework for anything to exist, hadn't yet manifested. 8 billion years removed from nothing. Let that settle into your bones. You are a pattern of atoms that briefly lights up with awareness, arising from a cosmos that itself arose from what? A quantum fluctuation? A mathematical necessity? A previous universe? Or simply a boundary beyond which the question dissolves into incoherence? Every memory you have, every dream, every hope, every fear, all of it traces back through an unbroken chain of causation to that first moment. The neurons firing in your brain right now are the result of chemical processes, which are the result of evolutionary processes, which are the result of planetary formation, which is the result of stellar nucleosynthesis, which is the result of galaxy formation, which is the result of quantum fluctuations in the inflationary epoch, which is the result of what? The chain ends or loops, or dissolves into quantum uncertainty, but it doesn't extend infinitely backward in any simple way. And if that's true, then every human being who has ever lived, every thought that's ever been thought, every emotion ever felt, every civilization that's risen and fallen, all of it emerged from that boundary. All of consciousness, all of meaning, all of purpose, all of love and suffering and beauty and terror, these things have existed for only the briefest cosmic moment in a universe that might cycle eternally, or might exist as one bubble among infinite bubbles, or might simply be without explanation or cause. This is the existential weight of cosmology. This is what it means to really understand, not just intellectually, but emotionally, viscerally, that the universe had an origin, and that origin is fundamentally mysterious. You are not separate from this mystery. You are inside it, made of it, constituted by it. Think about your childhood. You have memories, perhaps vivid ones. Your first day of school, learning to ride a bike, a family vacation, a moment of joy or embarrassment or wonder. These memories feel real, feel solid, feel like they really happened. But quantum mechanics suggests that the past isn't fixed until it's observed. John Wheeler proposed a series of delayed choice experiments showing that measurements made now can affect which path a particle took in the past. The particle doesn't have a definite history until you force it to by measuring it. Now extend this to the cosmos. The entire history of the universe might be quantum mechanical in the same way. The past might not be fully determined, fully real, until it becomes entangled with the present. Your act of remembering might be participating in making the past real, in collapsing the quantum wave function of history. This sounds like philosophical speculation, but it's grounded in serious interpretations of quantum mechanics. The past, in some sense, might not exist independently of your observation of it. The universe's history might be constantly being written and rewritten as quantum measurements occur, as the wave function collapses, as potentiality crystallizes into actuality. If that's true, if even part of that is true, then your memories aren't just records of what happened. They're participating in making what happened real. You're not just observing history, you're creating it, retroactively, by the act of remembering. And this applies to the cosmic past too. The observations we make now, measuring the cosmic microwave background, detecting gravitational waves, analyzing the light from distant supernovae, these observations might be participating in making cosmic history real, in determining which quantum branch of the universe's wave function we inhabit. This is deeply unsettling. It violates every intuition about the relationship between past, present, and future. It suggests that reality is far more fluid, far more observer-dependent than classical physics ever imagined. But it gets stranger still. If the multiverse is real, if there are infinite universes with every possible variation, then somewhere, in some bubble universe, there's another version of you, not similar to you, not analogous to you. Actually you with the same atomic configuration, the same memories, the same thoughts, experiencing the same moment. This isn't science fiction. This is a mathematical consequence of infinity. In an infinite multiverse with random variations, every possible configuration occurs not just once, but infinitely many times. Every arrangement of atoms that could constitute you will be realized somewhere. Every moment you're experiencing now is being experienced by infinite copies of you scattered across the multiverse. And not just you as you are now. Every possible version of you, every choice you didn't make, every path you didn't take, exists somewhere. There's a universe where you made different decisions, where you live in a different city, have a different career, love different people, where you died in childhood, where you never existed because your parents never met. All of these versions are equally real. They all exist with the same ontological status as this version, the one reading these words. You are not unique. You are one instance of an infinite ensemble, most of whom you'll never meet, never communicate with, never even know exist. This is the terrifying implication of infinity. Once you accept that space might be infinite, or that the multiverse might be infinite, or that time might be infinite, you have to accept that everything that can happen does happen, infinitely many times. Your life, in all its uniqueness and specificity, is being lived right now by infinite other yous. Every triumph you'll ever experience, someone else you is experiencing it too. Every tragedy, every loss, every moment of joy, replicated infinitely across the cosmic ensemble. Does this make your experiences less meaningful or more meaningful? If every possible version of your life exists, does that mean your choices don't matter? Or does it mean that every choice branches reality, creates new universes, and therefore carries infinite weight? There's no consensus answer. Some philosophers argue that infinite replication trivializes existence. If everything happens, then nothing is special. Others argue that it amplifies meaning. Every action you take is replicated infinitely, its consequences spreading across the multiverse. But both perspectives share a common recognition. You are not the center of reality. You're not even unique within reality. You're one instance of a pattern that might be instantiated infinite times across infinite space, or infinite bubbles, or infinite cycles. And now consider this. If the universe is truly eternal, either through cyclic cosmology or eternal inflation, then this moment, this exact configuration of atoms that constitutes you reading these words, will occur again. Not similar configurations, this exact one. In an infinite timeline, every possible arrangement of matter will eventually recur. This is called the Poincaré recurrence theorem, and it applies to any finite system given infinite time. Your entire life, every moment of it, will be lived again. Not by a descendant, not by someone in the far future who happens to resemble you. By you, in the most literal sense, the exact same arrangement of particles, producing the exact same thoughts and experiences, and it will happen not just once, but infinitely many times. You've lived this life before, infinite times before, and you'll live it again, infinite times again. You have no memory of the previous iterations. Each time feels like the first time. Each cycle is subjectively unique, even though it's cosmically identical. You'll read these words again, think these thoughts again, experience this same moment of existential vertigo again, infinitely many times across infinite cosmic cycles. This is Nietzsche's eternal return, transformed from philosophical thought experiment into potential cosmic reality. The cosmic version isn't a choice. It's just a feature of eternal time combined with finite configurations. Does this make your current experience an illusion? A dream that the universe keeps dreaming? Or does it make every moment infinitely precious, since you'll be locked into this pattern forever? Again, there's no clear answer. But the question itself does something to your sense of self. It destabilizes the feeling that you're living through a unique, unrepeatable narrative. It suggests instead that you're caught in an eternal loop, a cosmic repetition, a pattern that will play out again and again without end. This is what it means to truly absorb the implications of cosmology, not just to understand the equations, but to feel what they mean for your existence. To recognize that the cosmic story isn't separate from your story, that the questions about the origin of the universe are questions about the origin of you, that the mystery of existence isn't out there among the galaxies. It's here, in your consciousness, in this present moment. You are the universe becoming aware of itself. This isn't poetic metaphor. This is literal truth. The atoms in your body were forged in stars. The energy powering your thoughts came originally from the Big Bang, filtered through billions of years of cosmic evolution. Your consciousness is a local manifestation of the universe's own complexity, a region where matter has organized itself in such specific ways that it can reflect on its own existence. And what you're reflecting on, what you're feeling right now as you read these words, is the weight of that existence, the strangeness of it, the impossibility of it, the fact that there's something rather than nothing, and that the something includes you briefly, mysteriously, inexplicably. There's a moment that comes to every person who seriously contemplates these ideas, a moment when the comfortable abstractions fall away and you're left facing the raw fact of existence. Not existence in general, your existence. The fact that you are here, now, aware, experiencing, when you could so easily not be. When for the vast majority of cosmic history, you weren't. When in the vast majority of possible universes, if there are other universes, you don't exist. You are cosmically improbable. Statistically impossible, really. The specific arrangement of atoms that makes you requires such precise initial conditions, such exact evolutionary history, such unlikely coincidences, that if you could calculate the probability, it would be a number with more zeros after the decimal point than there are particles in the observable universe. And yet here you are. Impossible but actual. Improbable but real. This is called the anthropic principle in cosmology. But it's more than an abstract selection effect. It's a deeply personal fact about your existence. You find yourself in a universe capable of producing you because only in such a universe could you exist to find yourself. It's a tautology, but it's a tautology with profound emotional resonance, because it means that in some sense the universe, or at least the part of it you inhabit, the branch of the wave function you're on, the bubble you occupy, is fine-tuned for your existence. Not because it cares about you, not because you're special, but because you're the kind of pattern that can only emerge in a very specific cosmic context. If the cosmological constant were slightly different, galaxies wouldn't form. If the strong nuclear force were slightly weaker, complex atoms couldn't exist. If the electron mass were different, chemistry would work differently, and life as we know it would be impossible. The universe sits on a knife's edge of parameters. Change any one of dozens of fundamental constants by even a small amount, and you get a sterile cosmos. No stars, no planets, no chemistry, no evolution, no consciousness, no you. Why? Why is the universe this way? If there's only one universe, it's a staggering mystery. It looks designed, fine-tuned, optimized for life, but by whom? By what process? Natural selection doesn't apply to universes. There's no mechanism for tuning constants. It seems like an impossible cosmic coincidence. If there's a multiverse, the mystery dissolves, but into something equally strange. Yes, most universes are sterile. Yes, we necessarily find ourselves in a rare, life-permitting universe, but that means we're living in the cosmic equivalent of winning an infinite lottery. We drew the one-in-infinity winning ticket, and we can never know what all the other tickets looked like, can never verify that they really exist, can never test whether the multiverse explanation is true or just a way of avoiding the fine-tuning problem by postulating infinite, unobservable entities. Either way, you're left with mystery. Either one inexplicable universe or infinite, unobservable universes. Either design without a designer or selection without verification. And in the middle of this cosmic mystery, you exist, temporarily, briefly. A flash of consciousness in an ocean of entropy. You'll live for a few decades if you're lucky. The universe will exist for trillions upon trillions of years into the future, slowly dissipating, stars burning out, black holes evaporating, until there's nothing left but cold, dark, empty space filled with the faint whisper of photons stretched to infinite wavelengths. Your entire existence, the entire existence of humanity, of Earth, of the Sun, of the Milky Way, is a brief flicker near the beginning of cosmic history. You're closer in time to the Big Bang than to the ultimate heat death. You exist in the universe's youth, in the brief window when stars shine and planets form and chemistry happens and life emerges. Eventually, there will be a last thought by a last conscious being. After that, the universe will continue for incomprehensible ages, but there will be no one to observe it, no one to wonder about it, no one to ask questions about its origin. Unless consciousness re-emerges somehow, unless in the far, far future quantum fluctuations in the vacuum spontaneously assemble into complex structures, Boltzmann brains that briefly flicker into awareness before dissolving back into chaos. Unless the universe cycles and life emerges again in the next iteration. Unless there are other universes, other bubbles, where consciousness continues long after it's ended here. But from your perspective, from the perspective of this particular instance of consciousness reading these words, the end is certain. You will die. Humanity will die. The Earth will die. The Sun will die. The galaxy will die. Everything you've ever known or loved or cared about will dissolve back into the universal heat death. This is the ultimate existential truth that cosmology reveals. Impermanence. Not just your impermanence, not just humanity's impermanence, but the impermanence of everything. Stars, galaxies, space-time itself, all temporary patterns in an ocean of entropy, briefly emerging into complexity before dissolving back into equilibrium. Some find this terrifying. Others find it liberating. If nothing lasts forever, if everything eventually returns to the void, then perhaps the pressure to find ultimate meaning, cosmic purpose, eternal significance, perhaps that pressure can be released. Perhaps you can find meaning in the temporary, in the local, in the brief flowering of complexity that is your life and your civilization. Perhaps the fact that you exist at all, against such impossible odds, in such a brief window of cosmic history, is enough. Perhaps the experience of consciousness, of love, of beauty, of wonder. Perhaps these things are meaningful precisely because they're temporary, because they won't last, because this moment right now will never occur again unless the universe truly cycles, but even then you won't remember. Or perhaps that's just a comforting story we tell ourselves. Perhaps the real truth is darker, colder, more indifferent. Perhaps the universe is exactly what it appears to be, a vast, unconscious machine, operating according to impersonal laws, producing consciousness as a brief, accidental byproduct before grinding on toward heat death. Perhaps there is no meaning, no purpose, no significance beyond what we temporarily project onto the void. Cosmology can't answer these questions. Science describes what is, not what matters. It can tell you how the universe evolved, but not whether that evolution has purpose. It can calculate the probability of your existence, but not whether that existence has value. You have to make those determinations yourself. You have to decide what it means to exist in a universe that emerged from quantum foam, that might be one of infinite copies, that will eventually die a cold, entropic death. You have to find meaning in meaninglessness, purpose in contingency, significance in the midst of cosmic indifference. This is the existential crisis that honest cosmology provokes. And here's the terrifying truth. You're not guaranteed answers. You're not even guaranteed that the questions are coherent. You might spend your entire life searching for cosmic meaning only to discover that meaning is a human projection, a psychological need, an evolutionary adaptation with no cosmic correspondent. Or you might find something, some sense of connection to the whole, some feeling of participation in the cosmic story, some way of understanding your brief existence as meaningful despite its impermanence. But that finding, if it comes, won't come from physics equations. It will come from somewhere deeper, somewhere more personal, somewhere that science can illuminate, but never fully explore. Because in the end, the mystery isn't just about the universe. It's about consciousness. About the fact that matter can organize itself into patterns that wonder about their own origin. You are such a pattern. Temporary, improbable, self-aware. Made of stardust and quantum fields, evolved through billions of years of cosmic history, briefly capable of contemplating the whole incomprehensible structure. And what you're contemplating, what you're feeling right now, is the weight of existence itself, the strangeness of being, the vertigo of standing at the edge of knowledge and peering into the abyss of unknowing. This is cosmic horror, but not in the sense of monsters and terrors. Cosmic horror in the sense of confronting realities too vast, too strange, too fundamentally other for human minds to fully grasp. The horror of realizing that you're smaller than you thought, more contingent than you imagined, more temporary than you wanted to believe, but also, and this is crucial, more miraculous than you dared hope. Because despite all the improbability, despite the cosmic indifference, despite the eventual heat death, despite the fundamental mysteries that will never be solved, despite all of this, you exist. You are aware. You can experience beauty and love and wonder. You can ask questions about the origin of everything. You can hold in your mind, simultaneously, the vastness of cosmic space and time and the intimacy of your own immediate experience. You are the universe contemplating itself. And in that contemplation, in that moment of reflexive awareness, something extraordinary happens. The universe becomes meaningful because there's someone to find meaning in it. Reality becomes beautiful because there's someone to perceive beauty. The cosmic story becomes a story because there's someone to tell it, someone to listen, someone to care. This doesn't solve the mystery. It doesn't answer the question of what came before or why anything exists. But it transforms the nature of those questions. It makes them personal rather than purely abstract. It stakes your existence on the answer or on the perpetual lack of answer. And maybe that's the point. Maybe the mystery of existence isn't meant to be solved. Maybe it's meant to be lived, experienced, felt in the bones and blood and neurons of conscious beings who emerge briefly from the quantum foam and return to it, who shine for a moment like stars before burning out. You are living the mystery right now, not thinking about it, not studying it, living it. Your existence is the universe's answer to the question of why there's something rather than nothing. Not a verbal answer, not an explanatory answer, but an existential answer. The universe produces consciousness, and consciousness asks why, and the asking itself is part of the answer. This is the weight you're carrying, the weight of being a conscious pattern in an unconscious cosmos, the weight of asking unanswerable questions, the weight of existing temporarily in an indifferent universe. And the weight is both crushing and exhilarating. Crushing because it reveals your insignificance. Exhilarating because it reveals your participation in something infinitely larger than yourself. You are cosmically insignificant and cosmically essential, both at once. A meaningless arrangement of atoms, and the only thing that can create meaning from that arrangement. This is what it means to be human at the edge of cosmic knowledge. To know enough to see the abyss, not enough to see across it. And in that transformation, something shifts. The cosmic story becomes your story. The origin of the universe becomes the origin of you. The mystery of existence becomes the mystery of your particular existence. In this moment, reading these words, feeling whatever you're feeling, you can't unknow what you now know. You can't return to comfortable certainty. You've seen the edge. You've felt the vertigo. You've confronted the possibility that your entire existence, past, present, and future, emerged from quantum uncertainty and will dissolve back into it. And now you have to live with that knowledge, carry it forward, integrate it somehow into your daily life, your relationships, your sense of purpose. How do you do that? How do you eat breakfast and go to work and love people and plan for the future when you've internalized the truth that the universe emerged from nothing, means nothing, and will eventually collapse back into nothing? The answer is different for everyone. Some find solace in religion, in the idea that the cosmic mystery points toward transcendent meaning. Some find purpose in human connection, in creating pockets of warmth and light in an indifferent universe. Some embrace absurdism, acknowledging the meaninglessness while choosing to create meaning anyway. Some retreat into nihilism, concluding that nothing matters and acting accordingly. But whatever answer you find, you'll find it here, in the existential space between cosmic mystery and human experience, between the equations that describe the universe and the emotions that constitute your inner life, between the objective truth of cosmology and the subjective truth of consciousness. This is where you live. This is where everyone lives. At the intersection of the cosmic and the personal, the infinite and the immediate, the eternal and the temporary. The universe doesn't owe you answers, but it has given you something more precious, the ability to ask questions, to wonder, to contemplate mysteries larger than yourself. And in that contemplation, in that wondering, you become more than just a pattern of atoms. You become a meaning maker, a consciousness capable of grasping, however imperfectly, the magnitude of existence itself. This is the gift and the curse of cosmic awareness. The gift of seeing further than any organism has a right to see. The curse of seeing so far that you glimpse the edge of the knowable. And at that edge you find not answers but yourself reflected back, asking the eternal question, why? There's a question that physicists don't like to ask out loud. They'll discuss it in late-night conversations at conferences after a few drinks, when the formal presentations are done and the masks come off. They'll hint at it in the acknowledgement sections of papers, buried in polite academic language. But they rarely confront it directly, publicly, because it sounds too philosophical, too unscientific, too much like giving up. The question is this: what if the universe is fundamentally paradoxical? What if reality operates according to rules that are logically contradictory, and our failure to resolve these contradictions isn't a temporary gap in knowledge, but a permanent feature of existence itself? This isn't idle speculation. This is a genuine possibility emerging from multiple directions in modern physics. Quantum mechanics produces logical paradoxes, particles that are waves, cats that are simultaneously alive and dead, measurements that retroactively determine the past. General relativity produces paradoxes, black holes where time stops, singularities where physics breaks, closed time-like curves where you could theoretically travel into your own past. And when you combine the two, when you try to understand the quantum mechanics of space-time itself, the paradoxes multiply. Time that might not exist. Causation that might be circular. Existence that might not require a cause. These aren't problems to be solved. They might be features to be accepted. The universe might not make sense in the way human logic demands. It might operate according to principles that are fundamentally alien to our evolved intuitions about how reality should work. And nowhere is this more apparent than at the origin of everything, where every attempt to explain what came before produces new paradoxes, new impossibilities, new ways that reality refuses to conform to our expectations. Let's start with the most obvious paradox, the paradox of the first cause. Everything that exists has a cause. This seems self-evident. You exist because your parents existed. Your parents existed because their parents existed. Earth exists because the solar nebula collapsed. The solar nebula existed because a previous generation of stars died. Those stars existed because galaxies formed. Galaxies formed because of density fluctuations in the early universe. Trace this chain of causation backward, and eventually you reach the Big Bang. And then you ask, what caused the Big Bang? If everything needs a cause, then the Big Bang needs a cause. But that cause would itself need a cause, and that cause would need a cause, in an infinite regress that never reaches solid ground. This is the cosmological argument that philosophers have debated for millennia. You can't have infinite regress, they say, so there must be a first cause, an uncaused cause, something that exists without explanation. But physics rebels against this. Physics is about explanation, about finding causes, about tracing effects back to their origins. An uncaused cause isn't a physical explanation. It's a placeholder, a name for ignorance, a way of saying the chain of explanation stops here without saying why. So you have two equally unpalatable options. Either causation extends infinitely backward, with no beginning, no first cause, just an endless chain of causes and effects stretching into an infinite past. Or causation has a beginning, a first cause that itself has no cause that exists without explanation. Both options violate intuition. Both seem logically problematic, and both might be wrong, because the real solution might be even stranger. Causation itself might not apply at the origin of time. Remember what we discussed earlier. Causation is a temporal concept. Causes precede effects in time. But if time itself begins at the Big Bang, then there's no before for a cause to exist in. The Big Bang doesn't have a cause in the normal sense because causation requires time, and time begins with the Big Bang. This sounds like a clever way out of the paradox, but it's not really a solution. It's a restatement of the mystery. You're saying that the universe simply began without cause, without precedent, without explanation. It's not that something caused the Big Bang, it's that the Big Bang is the beginning of causation itself. But this raises a new question. Why did time begin? Why is there a universe with time and space and matter and energy rather than just nothing? Saying time began at the Big Bang doesn't explain why there's a Big Bang at all. It just pushes the question back one level. Some physicists appeal to quantum mechanics. In quantum theory, things can happen without cause. Radioactive decay is genuinely random. There's no hidden variable determining when a particular atom will decay. Quantum tunneling allows particles to appear in places they shouldn't be able to reach classically. Virtual particles pop into existence from the quantum vacuum without any cause. So maybe the universe is the same. Alexander Vilenkin's universe from nothing proposal works exactly this way. The wave function of the universe includes contributions where the universe tunnels from a state of zero size into an inflating state. It's a quantum event, governed by probabilities rather than certainties, happening without any classical cause. But this just moves the mystery. Now you're asking, why does quantum mechanics exist? Why is there a quantum vacuum with specific properties that allow universes to tunnel into existence? Why those laws, those rules, those mathematical structures? You can appeal to the multiverse. Maybe all possible quantum laws exist somewhere. We find ourselves in a universe with these particular laws because only these laws allow observers to exist. This is anthropic reasoning, and it dissolves the fine-tuning problem by saying that every possibility is realized somewhere. But the multiverse doesn't solve the ultimate question, it just inflates it. Instead of explaining existence, you've multiplied it infinitely and claimed that no further explanation is needed. And maybe that's right. Maybe existence is a brute fact, something that requires no explanation, something that simply is because it must be. Maybe existence doesn't have a reason. It's just the baseline, the starting point, the foundation that everything else rests on, but which itself rests on nothing. This is unsatisfying. Humans crave explanation. We want to know not just how things work, but why they work that way. We want ultimate answers, final truths, foundations that themselves are founded on something comprehensible. But the universe might not care what we want. Reality might simply be inexplicable at the deepest level. Not inexplicable because we're not smart enough or haven't gathered enough data. Inexplicable because explanation itself has limits. Because the chain of reasons must end somewhere, because you can't derive existence from non-existence or something from nothing. This is the paradox of the first cause. You need a beginning, but beginnings need causes. But causes need time, but time begins at the beginning. It's a logical circle, and every attempt to break out of it just creates a new version of the same circle at a deeper level. Now consider a different paradox. The paradox of cosmic fine-tuning. The universe is exquisitely balanced. If the cosmological constant were larger by just 1 part in 10 to the 120, space would expand so rapidly that galaxies could never form. If it were smaller or negative by a similar amount, the universe would recollapse before stars could ignite. If the strong nuclear force were a few percent weaker, atomic nuclei would fly apart. If it were a few percent stronger, all hydrogen would have fused into heavier elements in the early universe, leaving no fuel for stars. The electron mass, the fine structure constant, the ratio of electromagnetic to gravitational force strength, the initial density fluctuations. Dozens of parameters must fall within narrow ranges for a universe capable of supporting complexity, let alone life. This is disturbing. It looks designed. It looks like someone tuned the dials specifically to create a universe where stars shine, planets form, chemistry happens, evolution occurs, consciousness emerges. But who's the tuner? What's the mechanism? How does a universe get fine-tuned without a tuner? The multiverse provides one answer. If there are infinite universes with random variations in physical constants, then most are sterile, lifeless, structureless, boring. But a tiny fraction, by pure chance, will have the right combination of parameters to support complexity. We necessarily find ourselves in one of those rare universes because only in such universes do observers exist to find themselves anywhere. This is anthropic reasoning, and it works, sort of. It explains the fine-tuning without invoking a designer, but at a cost. The cost is accepting the existence of infinite, unobservable universes. You're explaining one universe by postulating infinitely many others that you can never see, never test, never verify. Is this science, or is it metaphysics dressed in scientific language? Critics argue that the multiverse is unfalsifiable. If you can never observe the other universes, how can you ever confirm or deny their existence? Proponents respond that many scientific theories involve unobservable entities. Quarks are never seen in isolation. But we believe they exist because of indirect evidence. Maybe the same will be true for the multiverse. Maybe we'll find indirect signatures, subtle patterns in the cosmic microwave background, or anomalies in fundamental constants that point toward a larger multiverse. But even if the multiverse exists, it doesn't fully resolve the fine-tuning paradox. It just transforms it. The meta-laws that govern the multiverse, the rules that determine how bubble universes form, what ranges of constants they can have, how they interact, these meta-laws would themselves need to be fine-tuned to produce the observed outcome. You can postulate a meta-multiverse where even those meta-laws vary, but this is an infinite regress. At some level, you have to accept that the fundamental structure of reality, whatever it is, simply is, without further explanation. Or maybe you take a different approach. Maybe the universe isn't fine-tuned at all. Maybe what looks like fine-tuning is actually selection bias. We observe a universe with these particular constants because we're made of matter that can only exist with these constants. If the constants were different, different kinds of complexity might emerge. Different kinds of observers might exist, and they'd marvel at how their universe seems fine-tuned for them. This is a nice idea, but it doesn't hold up under scrutiny. Most variations of fundamental constants don't produce alternate forms of complexity. They produce universes that are genuinely sterile. No stars, no chemistry, no structure beyond random thermal noise. The range of parameters that allows any form of complexity is genuinely narrow. It's not that we're anthropocentrically assuming only our kind of life counts. It's that most parameter combinations don't allow any kind of life, any kind of complexity, any kind of structure that could conceivably support observation or consciousness. So the fine-tuning is real. The question is what it means. Design, multiverse, coincidence? Some fourth option we haven't thought of yet? Lee Smolin proposed an intriguing alternative: cosmological natural selection. Maybe universes reproduce through black holes. Maybe every black hole that forms spawns a new universe on the other side of the singularity. A baby universe with slightly mutated physical constants. Universes that produce lots of black holes will have lots of offspring. Over many generations, you'd get selection for universes optimized to produce black holes. And here's the twist: the conditions that produce lots of black holes overlap substantially with the conditions that support life. Stars, supernovae, dense stellar remnants. The same astrophysics that makes black holes also makes planets and complex chemistry. So our universe might be fine-tuned not for life specifically, but for black hole production. And life is a side effect. It's a clever idea. It provides a mechanism, natural selection, that can produce apparent fine-tuning without requiring design or infinite multiverses. But it has problems. How do universes reproduce through black holes? What does it even mean for a new universe to exist on the other side of a singularity? How are the constants transmitted and mutated? And crucially, how do you test this? What observations would confirm or refute cosmological natural selection? So far, no one has answers. The theory remains speculative, intriguing, but unproven. And so the paradox remains. The universe appears fine-tuned, or requires speculative mechanisms that can't be tested. Cosmological natural selection. You're trapped. Every direction you turn, you find either infinite regress, unfalsifiable claims, or brute facts that have no explanation. The universe seems to resist giving up its ultimate secrets, to produce paradoxes wherever you probe most deeply. But perhaps the deepest paradox of all is the paradox of time itself. We experience time as flowing. The present moment moves forward from past toward future. The past is fixed, unchangeable, already determined. The future is open, uncertain, not yet decided. This feeling of temporal flow is so fundamental to consciousness that it's hard to imagine experience without it. But physics says time doesn't flow. In relativity, space-time is a four-dimensional block. All moments, past, present, future, exist simultaneously. There's no objective now that moves through time. Different observers will disagree about which events are simultaneous. The flow of time is an illusion, an artifact of consciousness, not a feature of physical reality. Yet quantum mechanics seems to preserve a distinction between past and future. The wave function evolves forward in time according to the Schrödinger equation. Measurements collapse the wave function, creating irreversible changes. The arrow of time, the directionality from past to future, seems built into quantum mechanics in a way it's not built into relativity. But here's where it gets strange. The Schrödinger equation is time-symmetric. If you run it backward, you get perfectly valid physics. The arrow of time doesn't come from the equation itself. It comes from the measurement process, from the collapse of the wave function. And the collapse is mysterious, poorly understood, possibly not even real, depending on which interpretation of quantum mechanics you accept. In the many worlds interpretation, there's no collapse. The wave function never reduces. Instead, reality branches. Every quantum measurement creates a superposition of outcomes, and each branch of the superposition is equally real. You, your consciousness, only experience one branch, but all branches exist simultaneously in the vast superstructure of the universal wave function. In this view, the past isn't singular. There's no one definite history. There's a superposition of histories, all equally real, branching and diverging with every quantum event. Your memories are memories of one particular branch, but other versions of you in other branches have different memories, slightly diverged histories, alternate pasts. And the future isn't open or uncertain. It's already there, in the superposition, all possibilities realized simultaneously. Your experience of choosing, of determining the future, is an illusion. You're simply experiencing one branch among many, one thread in the vast tapestry of the universal wave function. This dissolves the distinction between past and future. Both are equally real, equally determined, equally part of the eternal structure of the wave function. Time doesn't flow, it's just there, all of it, simultaneously, and your consciousness moves through it, or rather exists at different points along your world line in different branches, creating the illusion of flow. But this creates new paradoxes. If all branches are real, then every possible outcome occurs. Every choice you make, you also make the opposite choice in another branch. Every tragedy that happens also doesn't happen somewhere else. Every death is balanced by a survival. Every ending is also a continuation. Does this make choices meaningless? If every decision branches reality, if you do everything possible across all branches, then what's the point of deliberation? Why agonize over decisions when you'll make every choice anyway? Or does it make choices infinitely meaningful? Because each choice determines which branch you, this particular instance of consciousness, will experience. The other yous in other branches are separate. They're not you in any experiential sense. So your choices still matter for determining your subjective future, even if all possible futures exist objectively. And what about the arrow of time? If the wave function just is, eternally existing in superposition, why do we experience time as flowing in one direction? Why do we remember the past, but not the future? Why does entropy increase, disorder spread, energy dissipate? The answer, according to thermodynamics, is the second law. Entropy always increases in closed systems. The universe evolves from ordered states to disordered states, from low entropy to high entropy. This creates an arrow of time, a directionality to temporal evolution. But this raises a new question. Why was the entropy so low in the early universe? Why did the universe begin in a highly ordered state? All matter and energy compressed into a tiny volume, ready to expand and evolve, rather than in a maximum entropy state, already at equilibrium, unable to evolve further. This is called the past hypothesis, and it's one of the deepest unsolved problems in cosmology. The Big Bang appears to violate the second law. It's a state of incredibly low entropy, from which the universe has been increasing in entropy ever since. But why? What set those initial conditions? What created that low entropy state? If you appeal to inflation, you're just pushing the problem back. What created the inflaton field in its low entropy, high energy state? If you appeal to quantum tunneling, you're saying the universe spontaneously jumped from nothing to a low entropy state. But low entropy states are rare, special, unlikely. Why would the universe tunnel into such an improbable state rather than a maximum entropy state? Roger Penrose calculated that the probability of the observed low entropy initial conditions is something like 1 in 10 or 10 while 123. This isn't just unlikely. It's inconceivably, impossibly unlikely. And yet it happened. Some physicists argue that low entropy is built into the boundary conditions. The Big Bang just is a low-entropy state, by definition. And asking why is meaningless. Others suggest that the multiverse provides an answer. Most universes have maximum entropy, but a tiny fraction have low entropy, and we necessarily find ourselves in one of those, because only low-entropy universes allow observers. But others propose something far stranger. Maybe the arrow of time isn't fundamental. Maybe it's emergent, appearing only at large scales, or in certain contexts. Maybe at the Planck scale, there's no distinction between past and future. Maybe time is symmetric, and the apparent arrow is a statistical effect, an artifact of our particular location in space-time, or our particular perspective as conscious observers. Carlo Rovelli has developed this idea extensively. He suggests that time, as we experience it, is an approximation, valid only when you're dealing with large numbers of particles, macroscopic systems, thermal environments. At the fundamental level, there's no time variable in the equations. There's only change, correlation, entanglement between degrees of freedom. What we call time is actually a measure of correlation. Systems become entangled with each other. This creates records, memories, traces of past states. And from these correlations, from the way different parts of the universe are entangled, something resembling time emerges. But it's not fundamental. It's not a flowing river carrying you from past to future. It's a web of correlations, a network of entanglements, a structure that emerges from the quantum state of the universe when you coarse-grain, when you ignore microscopic details and focus on macroscopic patterns. In this picture, asking what came before the Big Bang is asking about correlations that don't exist. The Big Bang is the boundary beyond which the correlation structure breaks down, beyond which the emergent notion of time ceases to apply. There's no before, because the correlations that constitute time don't extend beyond that boundary. It's elegant, it's philosophically sophisticated, and it's almost certainly untestable with current technology. We can't access the Planck scale where time becomes non-fundamental. We can't observe the quantum state of the universe directly. We're stuck inferring, extrapolating, hoping that our mathematics captures something true about reality. And this brings us to the most disturbing possibility of all. What if our mathematics doesn't capture reality? What if the equations we're using, the frameworks we're developing, the theories we're so proud of, what if they're just approximations, useful fictions, models that work in certain regimes but break down when pushed to extremes? This is the nightmare scenario for theoretical physics, that we've reached the limit not of observation, but of conceptualization. That the human mind, shaped by evolution to survive in a narrow range of environments, simply isn't capable of grasping the deepest truths about reality. That we're like medieval scholars trying to understand quantum mechanics, the concepts, the mathematics, the entire framework needed to comprehend the ultimate nature of reality might be forever beyond our cognitive reach. Some physicists dismiss this as defeatism. Of course we can understand reality, they say. We've come this far. We've decoded the atom, split the nucleus, photographed black holes, detected gravitational waves. Every generation of scientists has faced seemingly insurmountable problems and solved them. Why should this be different? But others take the possibility seriously. Human brains are biological computers, limited by neuron count, firing rates, architectural constraints. We can only hold so many concepts in working memory. We can only visualize so many dimensions. We can only perform calculations at a certain speed. These are hard limits, not temporary obstacles. And maybe, just maybe, the ultimate nature of reality requires cognitive capabilities we don't have. Maybe the theory of quantum gravity exists in some abstract Platonic realm, but our brains are too limited to fully grasp it. Maybe we can apprehend shadows of it, approximations, but never the thing itself. This would explain why progress has slowed, why we've been working on quantum gravity for decades without clear success, why every approach seems promising but incomplete. Maybe we're not failing. Maybe we're encountering a genuine cognitive limit, and we're too proud to admit it. Or maybe not. Maybe the next generation will have the breakthrough we've been missing. Maybe artificial intelligence, with different cognitive architecture, will see patterns we can't see. Maybe some brilliant teenager right now is doodling equations that will revolutionize physics in 20 years. The future is uncertain, but the present is clear. We don't know what came before the universe, and we might never know. Not because the information is hidden, but because the question itself might not have an answer that human minds can formulate, let alone understand. And yet we keep asking, keep probing, keep pushing against the boundary, because this is what consciousness does. It asks questions, even unanswerable ones. It seeks patterns, even in chaos. It demands meaning, even from indifference. Now let me tell you about the most unsettling theory in modern cosmology. It's not widely accepted. It's controversial, speculative, possibly wrong, but it's logically consistent, mathematically sophisticated, and philosophically profound. And if it's true, it changes everything about how we understand existence. The theory is this: the universe might already be dead, and we, all of us, everything we observe, every moment we experience, might be living in the last quantum echoes of a cosmos that has already reached its final state. Here's how it works. In quantum mechanics, observation affects reality. The act of measurement collapses the wave function, determining which of many possible outcomes becomes actual. Before measurement, particles exist in superposition, all possibilities simultaneously real. After measurement, only one possibility remains. Now extend this to cosmology. The universe is a quantum system. It exists in superposition, in a vast, complex, multi-dimensional wave function encompassing all possible histories, all possible states. Most of this wave function corresponds to maximum entropy states, dead universes, thermal equilibrium, nothing interesting happening. But a tiny corner of the wave function corresponds to low entropy states, universes with structure, with stars and galaxies, with complexity and life and consciousness. These states are astronomically rare in the space of all possible states, but they're not zero probability. They exist somewhere in the superposition. And here's the key insight. Conscious observers can only exist in the low entropy parts of the wave function. You can't have consciousness in thermal equilibrium. You need structure, organization, energy gradients, information processing. You need a universe far from equilibrium. So even though most of the wave function is dead, maximum entropy, featureless, boring, observers only ever find themselves in the tiny fraction that's alive. It's selection bias taken to the extreme. The overwhelming majority of reality is already at heat death. But observers, by definition, only inhabit the exceptional regions where life is possible. Now here's where it gets truly strange. In the far future, when the universe has expanded for trillions upon trillions of years, when all stars have burned out and all black holes have evaporated, and all that remains is cold, dark, empty space. Even then, quantum fluctuations continue. Virtual particles pop in and out of existence, and very, very rarely, a fluctuation will be large enough to create a complex structure, a galaxy, a star, a planet, a brain. These are called Boltzmann brains, conscious entities that spontaneously assemble from random quantum fluctuations in the vacuum. They exist for a brief moment, have a few experiences, maybe a few thoughts, then dissolve back into chaos. The probability of a Boltzmann brain forming is incredibly small, but in infinite time, incredibly small probabilities become certainties. Eventually, quantum fluctuations will create not just isolated brains but entire worlds, complete with false memories, fake histories, illusory pasts. And statistically, if the universe truly lasts forever, if heat death is followed by an eternity of quantum fluctuations, then Boltzmann brains vastly outnumber ordinary observers. For every real person who evolved on a real planet orbiting a real star, there will be quadrillions of Boltzmann brains that spontaneously fluctuate into existence with false memories of having evolved. So which are you? A real observer in a young universe? Or a Boltzmann brain in a dead universe with memories that never actually happened, living through the last few seconds before you dissolve back into quantum chaos? Statistically, if the universe is infinite into the future, you're almost certainly a Boltzmann brain. The probability that you're a real observer is vanishingly small compared to the probability that you're a random fluctuation. This is called the Boltzmann brain problem, and it's one of the strangest paradoxes in cosmology. It seems to imply that our most successful theories, thermodynamics, quantum mechanics, general relativity, predict that we're probably not real, that our experiences are probably illusions, that our memories are probably false. Some physicists argue this is a reductio ad absurdum. Any theory that predicts we're Boltzmann brains must be wrong. We know we're real. We know we evolved. We know we're not random fluctuations, so theories that predict otherwise need to be modified or abandoned. But how do you know? If you were a Boltzmann brain with false memories, you'd have no way to tell. Your memories would seem real to you. Your experiences would seem coherent. You'd believe you evolved on Earth, read books, learned science, just like you believe right now. There's no way to distinguish, from the inside, between being a real observer and being a Boltzmann brain. Both would produce the same subjective experience. So you can't use your experience as evidence. You can only appeal to probability. And probability says Boltzmann brains outnumber real observers by incomprehensible margins in an infinite future universe. The only way out is to argue that the universe won't last forever, that something, cosmic collapse, vacuum decay, some other catastrophic event, will terminate the universe before Boltzmann brains start to dominate, or to argue that consciousness requires more than just the right pattern of neurons, that there's something special about real brains that evolved through real history that Boltzmann brains lack. But both escape routes feel like special pleading. Like inventing epicycles to save a theory that's fundamentally flawed. And this leads to a darker thought. What if the universe already reached heat death? What if we're living trillions upon trillions of years in the future? In a dead cosmos, and our entire observable universe, all the galaxies, all the structure, all the apparent history, is just a quantum fluctuation? What if the Big Bang itself is a false memory? A pattern impressed on a Boltzmann universe that spontaneously appeared from chaos? This is almost certainly not true. The probability of fluctuating into our entire observable universe, with all its structure and consistency, is far, far smaller than the probability of fluctuating into a single Boltzmann brain. If we're fluctuations, we should observe maximum chaos, not the orderly cosmos we actually see. But the fact that the theory even allows this possibility, that it predicts the existence of Boltzmann observers at all, suggests something might be wrong with our understanding of cosmology, thermodynamics, or consciousness. Unless there's something we're missing. Some mechanism that suppresses Boltzmann brains, some feature of quantum gravity that prevents random fluctuations from producing complex structures, some deeper principle that explains why real observers vastly outnumber random fluctuations despite the apparent statistics. But we don't have that mechanism yet. We don't have that principle. We're left with the uncomfortable conclusion that our best theories predict we're probably not real. And the only reason we reject this conclusion is because we insist we know we're real, even though we can't prove it. This is the kind of paradox that keeps cosmologists awake at night. And it gets worse. Because there's another version of this problem that doesn't require Boltzmann brains at all. It's called the doomsday argument, and it uses pure statistics to predict that humanity probably won't last much longer. Here's the logic. Suppose humanity will eventually produce a total of n people across all of history, from the first humans to the last. You are one of those n people. Which position in the sequence are you most likely to occupy? If you have no other information, the answer is somewhere in the middle. It's unlikely you're one of the first few people. That's a small fraction of the total. It's unlikely you're one of the last few people. Also a small fraction. You're probably somewhere in the middle half, statistically speaking. Now here's the twist. Roughly 100 billion humans have lived so far. If humanity lasts for millions of years, spreading across the galaxy, there might be trillions or quadrillions of future humans. 0.01% of all humans who will ever exist. That's statistically unlikely. But if humanity goes extinct soon, say, in the next few centuries, then the total number of humans might only be, say, 200 billion. In that case, you're right in the middle. You're in the 50th percentile. That's statistically likely. Therefore, purely from your position in the sequence, you should predict that humanity won't last long. The doomsday argument suggests we're probably living in the final centuries of human existence, not the beginning of a millions-year civilization. This sounds insane. How can your birth order tell you when humanity will go extinct? But the logic is sound. Assuming you're a random sample from all humans who will ever exist. And if you're not random, what makes you special? Why should you expect to be unusually early in the sequence? The doomsday argument has been debated extensively. Some philosophers reject it as statistical sleight of hand. Others take it seriously, arguing it should genuinely update our estimates of existential risk. It's related to the Fermi paradox. Maybe we don't see other civilizations because civilizations tend to destroy themselves shortly after reaching technological maturity. Maybe we're in the final generations before some great filter wipes us out. Or maybe the argument is flawed. Maybe your position in the human sequence isn't random. Maybe consciousness or observation creates selection effects that invalidate the statistical reasoning. Maybe there's something special about being alive now, in this particular cosmic era, that breaks the symmetry the argument assumes. But you can't easily dismiss it. It's a genuine statistical argument, and statistics doesn't care about what you want to be true. If the reasoning is valid, it constrains your expectations about the future, whether you like it or not. And combined with the Boltzmann brain problem, it paints a disturbing picture. Maybe most conscious observers in the universe are either random fluctuations in dead universes or members of civilizations shortly before extinction. Maybe long-lived galaxy-spanning civilizations are so rare that statistically, you should expect to be in one of the doomed ones. Maybe we're living in the last century before nuclear war, or bioengineered plague, or artificial intelligence gone rogue, or climate collapse, or some other catastrophe wipes out humanity. And maybe that's not paranoia. Maybe that's just statistics, coldly calculating probabilities based on your position in the sequence. This is existential dread of a different kind. Not cosmic insignificance, but temporal urgency. Of course, statistics can be wrong. Predictions can fail. The doomsday argument might be flawed in some subtle way no one has identified yet. Humanity might beat the odds, spread across the stars, survive for millions of years. But the fact that our best statistical reasoning predicts doom, and the fact that we don't have a clear rebuttal except that can't be right, is sobering. It suggests that even if we solve all the mysteries about the Big Bang, even if we develop a theory of quantum gravity, even if we understand what came before the universe, we might not be around long enough to celebrate. Now let me tell you about one final paradox, the strangest and most fundamental of all. It's called the paradox of existence, and it's been haunting philosophers and physicists for centuries without resolution. The paradox is this: existence is impossible. But here we are. Every explanation for existence requires something to already exist. If you say the universe came from a quantum fluctuation, you're presupposing quantum mechanics. If you say it emerged from a multiverse, you're presupposing the multiverse. If you say God created it, you're presupposing God. If you say it's a mathematical structure, you're presupposing mathematics. But none of these are truly fundamental explanations. They all assume a prior framework: physical laws, mathematical structures, divine agency, something. And where did that framework come from? Either it has always existed, which means existence is eternal and unexplained, or it came from something else, which just pushes the question back. You can't get something from nothing. This seems logically certain. Nothing has no properties, no potential, no capacity to become something. By definition, nothing is the absence of everything. It can't have laws of physics, because laws are something. It can't have quantum fields, because fields are something. It can't even have logical or mathematical structure, because structure is something. So existence should be impossible. There should be nothing. Pure, absolute, eternal nothing. And yet here we are, existing, impossibly, inexplicably, imaginable, unthinkable, beyond conception. Maybe existence is necessary because non-existence is impossible. Maybe something must exist because nothingness can't, is backwards. But this feels like wordplay. Of course we can conceive of nothingness, at least as an abstract negation. No matter, no energy, no space, no time, no laws, no mathematics, no consciousness, no anything. That's nothingness. And it seems perfectly conceivable, even if we can't visualize it. Others argue that existence doesn't need an explanation. It's not that there's a deeper reason. It's just the way things are. Existence is a brute fact, the ultimate axiom from which everything else follows, but which itself follows from nothing. This is more honest than trying to explain existence by presupposing other things that exist, but it's deeply unsatisfying. It means that at the foundation of reality, there's just an unexplained fact. No reason, no cause, no mechanism. No, just, this is the way it is, and that's the end of discussion. And maybe that's the truth. Maybe reality really is founded on brute facts that have no deeper explanation. But it feels wrong. It feels like giving up. It feels like there should be a reason, even if we can't access it, even if it's beyond human comprehension. And this brings us to the final possibility, the one that almost no physicist wants to admit, but that might be unavoidable. Maybe the universe is fundamentally mysterious. Maybe there are truths about reality that are true but unprovable, facts that are real but inexplicable, aspects of existence that are inaccessible to any intelligence, no matter how advanced. This isn't mysticism. This is suggested by mathematics itself. Gödel's incompleteness theorems prove that any sufficiently complex formal system contains true statements that cannot be proven within that system. The system is incomplete. There are truths it can't access, even though they're true. If mathematics itself is incomplete, why should physics be complete? Why should we expect that the universe is fully comprehensible, that every question has an answer, that sufficient intelligence and sufficient data can decode everything? Maybe the origin of the universe is a Gödelian truth, real, definite, but forever beyond proof, forever beyond explanation, forever beyond understanding. Is asking a question whose answer exists but cannot be accessed from within the universe. Because the universe contains all information that can exist within the universe. And information about what's outside, what's before, what's beyond, might be fundamentally unavailable to any observer embedded in space-time. You're inside the system. You're made of the system. You're trying to understand the system from within. But the system might be structured such that certain truths about itself are hidden from internal observers. This is the darkest possibility. Not that we haven't found the answer yet, but that the answer is hidden by the structure of reality itself. That consciousness, anywhere, at any level of sophistication, is fundamentally barred from understanding its own ultimate origin. And if that's true, then the mystery isn't temporary. It's permanent. It's built into the architecture of existence, and will carry it with us forever. No matter how much we discover, no matter how far we progress, no matter how deeply we probe. The universe might be keeping secrets, not passively, not accidentally, but structurally, necessarily, unavoidably, and those secrets might include the answer to the most fundamental question we can ask. The shocking reveal. 9,000 words. But what if I told you that all of this, every paradox, every impossibility, every mystery, might be pointing toward a single shocking truth that almost no one has seriously considered? What if the universe isn't one thing? Not in the multiverse sense, where there are many separate universes, in a deeper sense. What if what we call the universe is actually multiple overlapping realities, multiple layers of existence, multiple ontological levels, and we're only aware of one of them? This sounds like science fiction, but it's emerging independently from several areas of cutting-edge physics. In string theory, there are extra dimensions, 6 or 7 of them, depending on the formulation. These dimensions are supposedly tiny, curled up, invisible. But what if they're not? What if they're full-sized, and we simply can't perceive them because our consciousness is somehow confined to the 3 spatial dimensions we're familiar with? What if there are beings, or simply other physical processes, existing in those other dimensions, moving through spaces we can't see, experiencing time in ways we can't imagine? They would be here, right now, occupying the same location as you, but in different dimensions, invisible, undetectable, utterly alien. And what if the Big Bang wasn't the beginning of all those dimensions? What if it was just the beginning of our particular 3-dimensional slice? What if the other dimensions have their own histories, their own beginnings, their own civilizations or physical processes unfolding according to rules we can't begin to fathom? This isn't pure speculation. In brain cosmology, a variant of string theory, our universe is a 3-dimensional brain embedded in a higher dimensional space called the bulk. There could be other brains nearby, separated from us by microscopic distances in the extra dimensions, but completely invisible because we're confined to our brain. Gravity, uniquely among the forces, can propagate through the bulk. That's why it's so much weaker than the other forces. Most of its strength is leaking into extra dimensions we can't access. And when brains collide in the bulk, they trigger big bangs, creating or renewing the universes living on those brains. So the Big Bang might not have been the beginning of everything. It might have been a collision event, our brain smashing into another brain, releasing enormous energy, initiating the cosmic evolution we observe. But the brains themselves, and the bulk they inhabit, might be far older, far stranger, far more complex than anything we can observe from our confined perspective. What came before the Big Bang? Other brain states, other collisions, other universes living and dying on other brains in the bulk, a vast multidimensional reality of which our universe is just one small, temporary feature. But it gets stranger, because there's another layer of reality that physics is beginning to uncover, one that might be even more fundamental than space-time itself. It's called the holographic principle, and it's one of the most profound discoveries in modern physics. The idea is this: all the information in a 3-dimensional region of space can be encoded on its 2-dimensional boundary. The volume is like a hologram, a 3-dimensional projection arising from information stored on a surface. This was discovered by studying black holes. When you throw matter into a black hole, the information about that matter seems to vanish behind the event horizon. But that violates quantum mechanics, which says information must be conserved. Where does the information go? The answer, surprisingly, is that it's stored on the event horizon itself, the two-dimensional surface surrounding the black hole. The horizon area increases proportionally to the amount of matter you throw in, and the information is encoded as microscopic quantum details on that surface. The black hole's interior is somehow a projection of information living on its boundary. And if this is true for black holes, it might be true for the universe as a whole. Our entire three-dimensional reality, all of space, all of time, all of matter and energy, might be a hologram, a projection arising from information encoded on a distant boundary. Where's the boundary? No one knows for sure. Some versions place it at the edge of the observable universe on the cosmic horizon. Others suggest it's on the boundary at infinity. Still, others propose that the boundary is in the past, at the Big Bang itself, with all of cosmic history encoded in the initial conditions. But the implications are staggering. If we're living in a hologram, then three-dimensional space isn't fundamental. It's emergent, arising from two-dimensional information. The way a holographic image arises from interference patterns on a photographic plate. And if space is emergent, then asking what came before the Big Bang is asking about the information state on the boundary. What encoded the hologram? What determined the initial conditions? What structure underlies the emergence of our three-dimensional reality? Maybe the answer is that the boundary, the true fundamental reality, exists outside of time. It's timeless, eternal, unchanging. And what we perceive as cosmic history, as temporal evolution, as cause and effect, is just our limited perspective on a timeless structure. We're patterns in the hologram, and patterns don't have free will to ask about their origin. They're determined by the information on the boundary. This is deeply unsettling. It means you might not be what you think you are. You might not be a three-dimensional being moving through time. You might be a pattern of information on a two-dimensional boundary, and your experience of being three-dimensional, of moving through time, of having agency and consciousness, all of that might be emergent, illusory, a shadow cast by information living in a space with one fewer dimension. And that might be unanswerable from within the hologram. You're the projection. You can't access the photographic plate. But let's go even deeper. Because there's evidence from quantum mechanics that suggests reality might have even more layers than we've discussed. In certain interpretations of quantum mechanics, particularly the von Neumann-Wigner interpretation, consciousness plays a fundamental role in collapsing the wave function. Physical systems exist in superposition until observed by a conscious being. Observation brings reality into definite form. Most physicists reject this interpretation as too anthropocentric, too mystical. But it keeps coming back, keeps showing up in attempts to solve the measurement problem. And some versions, like integrated information theory, propose that consciousness is a fundamental feature of reality, not reducible to physical processes, not eliminable through scientific reductionism. What if they're right? What if consciousness really is fundamental? What if reality has two levels? A physical level described by mathematics and equations, and a consciousness level that observes, experiences, and in some sense creates the physical level through observation. In this view, the universe isn't purely physical, it's psychophysical, a reality where consciousness and matter are two aspects of the same underlying something. Call it mind, call it consciousness, call it being. The label doesn't matter. And if consciousness is fundamental, then the Big Bang wasn't just a physical event, it was also a consciousness event. The emergence of physics was simultaneously the emergence of some primal form of awareness, some proto-consciousness that would eventually evolve into you, into me, into every sentient being that has ever existed. What came before the Big Bang? In this view, there was consciousness without content, pure awareness without anything to be aware of, the ground of being, the eternal witness, existing timelessly until it chose to become manifest, to create a universe, to experience itself through multiple perspectives. This sounds religious. It sounds like theology. But it's emerging from physics, from the attempt to understand quantum mechanics, from the refusal to accept that consciousness is irrelevant to fundamental reality, and it connects to something else, something that physicists rarely discuss publicly because it sounds too crazy. But in private, after a few drinks, they'll admit it. The universe shows signs of fine-tuning not just for life but for consciousness, for observers. The constants aren't just tuned to allow atoms and stars. They're tuned to allow complexity, information processing, the kind of structures that can support thought. The universe seems optimized not just for existence, but for awareness. Why? If the multiverse explains it, then why does our particular bubble have this property? If cosmological natural selection explains it, then why does black hole production correlate with consciousness? If it's just coincidence, then why such a striking coincidence? Unless consciousness is the point. Unless the universe exists in order to be observed. Unless reality requires witnesses to be fully real. This is the participatory anthropic principle, proposed by John Wheeler. Observers aren't passive recipients of an independently existing reality. They're participants, bringing reality into existence through observation. And reality needs observers, which is why it's fine-tuned to produce them. And the answer might be, nothing came before, because time itself is a structure that emerges from observation, from consciousness imposing order on the quantum chaos. You, your consciousness, your capacity to observe, might be participating in creating the past retroactively. The universe's history might be undetermined until you observe it, until you force quantum superpositions to collapse into definite states, until you draw a particular thread out of the infinite tapestry of possibility. This is mind-bending, but it's not mysticism. It's emerging from serious attempts to understand quantum mechanics, to resolve the measurement problem, to explain why observation matters in fundamental physics. And it suggests something profound. Maybe the universe isn't a thing that exists independently and then happens to produce consciousness as a side effect. Maybe consciousness is primary, and the physical universe is what consciousness looks like from the inside. Maybe you're not in the universe. Maybe the universe is in you, not you specifically, not your individual ego or personality, but the deeper consciousness that you're a manifestation of, the awareness that's looking out through your eyes, thinking your thoughts, experiencing your experiences. That consciousness might be universal. It might be the ground of all being, the substrate from which both mind and matter emerge. And the Big Bang might be the moment when that consciousness chose to become particular, to fragment into individual perspectives, to experience itself through multiple viewpoints. What came before the Big Bang? Undifferentiated consciousness, unity, the one becoming the many, the eternal choosing to experience time. I know how this sounds. Like philosophy, like mysticism, like I've abandoned science for speculation. But consider this. Every materialist explanation for consciousness has failed. We can't explain how neurons produce subjective experience. We can't derive qualia from physics. We can't solve the hard problem of consciousness through reductionism. Maybe that's because we're approaching it backwards. Maybe consciousness doesn't emerge from matter. Maybe matter emerges from consciousness. Maybe the physical universe is what consciousness looks like when observed from within, when measured, when collapsed from infinite possibility into definite form. And maybe the reason physics keeps running into paradoxes, wave-particle duality, observer effects, the measurement problem, quantum entanglement, is because it's trying to describe a fundamentally consciousness-based reality using purely materialist mathematics. Maybe the equations break down at the Big Bang, not because physics ends there, but because you've reached the boundary where the physical emerges from the conscious, where mathematics gives way to experience, where objective description becomes subjective awareness. Fidel de Sheikh de Bissamai feels like an unanswerable question, because the answer is consciousness, awareness, being. And those aren't things that exist in time. They're what time exists in. They're the ground from which temporal experience emerges. You can't ask what came before consciousness because consciousness is the precondition for before existing as a concept. Time is how consciousness experiences sequence. Causation is how consciousness structures experience. The physical universe is how consciousness objectifies itself, makes itself observable, creates a shared reality where multiple perspectives can interact. And the Big Bang, the moment when consciousness chose to become physical, when the one chose to become many, when eternity entered time, when the infinite became finite, not because it had to, because it wanted to, because existence is richer with multiple perspectives than with one, because love requires an other to love, because the game of reality is more interesting when played by many players than by one. I'm speculating now. I've moved beyond physics into metaphysics, beyond science into philosophy. But maybe that's appropriate. Maybe the origin of the universe is not a scientific question. Maybe it's a philosophical one, or a spiritual one, or a question that requires a framework larger than science provides. Science describes how things work, but it can't explain why those particular rules rather than others. It can't derive existence from non-existence. It can't get something from nothing without presupposing the framework that allows the getting. At some point, you hit bedrock, brute facts, unexplained explainers, foundations that have no deeper foundation. And maybe that bedrock is consciousness itself, not your individual consciousness, but consciousness with a capital C. The awareness that's experiencing reality through billions of perspectives simultaneously, that's playing every role in the cosmic drama, that is the universe rather than being in the universe. This isn't provable. It might not even be testable, but it resolves paradoxes that materialism can't touch. It explains fine-tuning without infinite multiverses. It explains consciousness without reducing it to neurons. It explains the participatory nature of quantum mechanics without splitting reality into infinite branches. Not with another physical state, but with something that's outside of time entirely, something eternal, present always, the ground of being from which all particular beings emerge and to which they return. You are that consciousness. Not in the sense that you, with your memories and personality, are eternal. In the sense that the awareness looking out through your eyes is the same awareness looking out through every pair of eyes. The same consciousness experiencing every moment, every life, every perspective. You are the universe experiencing itself. Is the universe asking about its own origin? Consciousness investigating consciousness? Being wondering why there's being rather than nothing. And maybe there's no answer. Maybe at the deepest level, existence is self-explanatory. Consciousness is self-evident. Being is self-caused. Maybe the universe doesn't come from anywhere. It simply is, eternally, timelessly, 8 billion years, is how that timeless being experiences itself temporally. The Big Bang isn't a moment in time. It's where time begins. And before the Big Bang is not an earlier time but a different kind of reality entirely. Timeless being, eternal consciousness, the ground of all existence. You wanted an answer. I've given you several: physical, mathematical, philosophical, metaphysical. But the truth is, I don't know which is correct. No one does. Maybe all of them are partially right. Maybe none of them are. Maybe the universe is fundamentally mysterious, and that mystery is not a problem to be solved, but a feature to be accepted. You are living inside the greatest mystery that exists, not out there among the galaxies, but here, in your own awareness. The fact that you exist, the fact that you can ask questions, the fact that there's something rather than nothing, and that something includes you. This is the ultimate revelation. The mystery isn't outside you, it's you. Embodied in flesh and blood and neurons. You are the universe asking about itself. And maybe that's enough. Maybe you don't need a final answer. Maybe the search itself, the wondering, the questioning, the probing at the edges of knowability. Maybe that's what consciousness is for. Not to find answers, but to ask questions. Not to solve mysteries, but to live them. You are the mystery. You are the answer. You are the question. And somewhere, in another quantum branch, in another bubble universe, on another brain floating through the bulk, in another dimension perpendicular to the ones you can perceive, another version of you is having this exact same realization right now. Because if the universe is infinite, then this moment is happening infinitely. You are reading these words infinitely. You are understanding this truth infinitely. And every one of those infinite yous is alone with the mystery, staring into the abyss, feeling the weight of existence and choosing, somehow miraculously, to continue, to keep asking, to keep wondering, to keep being. Because that's what consciousness does. It exists, it questions, it persists. And in that persistence, in that refusal to accept easy answers, in that demand to know even when knowing seems impossible, in that you touch something eternal, not the eternity of infinite time, the eternity of being itself, the ground from which you came and to which you'll return. What came before the universe? Maybe you did. The consciousness reading these words, the awareness having these thoughts, maybe that's what's fundamental. Maybe that's what's eternal. Maybe you're not asking where the universe came from. Maybe the universe is asking where you came from. And the answer is nowhere. And everywhere. And always. You simply are. And that might be the only answer there is.